Chapter 11: Communication and Navigation. Introduction. With the mechanics of flight secured, early aviators began the tasks of improving operational safety and functionality of flight. These were developed in large part through the use of reliable communication and navigation systems. Today, with thousands of aircraft aloft at any one time, communication and navigation systems are essential to safe, successful flight. Continuing development is occurring. Smaller, lighter, and more powerful communication and navigation devices increase situational awareness on the flight deck. Coupled with improved displays and management control systems, the advancement of aviation electronics is relied upon to increase aviation safety. Clear radio voice communication was one of the first developments in the use of electronics in aviation. Navigational radios soon followed. Today, numerous electronic navigation and landing aids exist. Electronic devices also exist to assist with weather, collision avoidance, automatic flight control, flight recording, flight management, public address, and entertainment systems. Avionics in aviation maintenance. Avionics is a conjunction of the words aviation and electronics. It is used to describe the electronic equipment found in modern aircraft. The term avionics was not used until the 1970s. For many years, aircraft had electrical devices, but true solid-state electronic devices were only introduced in large numbers in the 1960s. Airframe and engine maintenance is required on all aircraft, and is not likely to ever go away. Aircraft instrument maintenance and repair also has an inevitable part in aviation maintenance. The increased use of avionics in aircraft over the past 50 years has increased the role of avionics maintenance in aviation. However, modern solid-state digital avionics are highly reliable. Mean times between failures are high, and maintenance rates of avionics systems compared to mechanical systems are likely to be lower. The first decade of avionics proliferation saw a greater increase in the percent of cost of avionics compared to the overall cost of an aircraft. In some military aircraft with highly refined navigation, weapons targeting and monitoring systems, it hit a high estimate of 80% of the total cost of the aircraft. Currently, the ratio of the cost of avionics to the cost of the total aircraft is beginning to decline. This is due to advances in digital electronics and numerous manufacturers offering highly refined instrumentation, communication, and navigation systems that can be fitted to nearly any aircraft. New aircraft of all sizes are manufactured with digital glass flight decks, and many owners of older aircraft are retrofitting digital avionics to replace analog instrumentation and radio navigation equipment. The airframe and power plant A&P maintenance technician needs to be familiar with the general workings of various avionics. Maintenance of the actual avionics devices is often reserved for the avionics manufacturers or certified repair stations. However, the installation and proper operation of these devices and systems remains the responsibility of the field technician. This chapter discusses some internal components used in avionics devices. It also discusses a wide range of common communication and navigational aids found on aircraft. The breadth of avionics is so wide that discussion of all avionics devices is not possible. History of avionics. The history of avionics is the history of the use of electronics in aviation. Both military and civil aviation requirements contributed to the development. The First World War brought about an urgent need for communications. Voice communications from ground to air and from aircraft to aircraft were established. Figure 111. The development of aircraft reliability and use for civilian purposes in the 1920s led to increased instrumentation and set in motion the need to conquer blind flight, flight without the ground being visible. Radio beacon direction finding was developed for en route navigation. Toward the end of the decade, instrument navigation combined with rudimentary radio use to produce the first safe blind landing of an aircraft. In the 1930s, the first all-radio-controlled blind landing was accomplished. At the same time, radio navigation using ground-based beacons expanded. Instrument navigation certification for airline pilots began. Low and medium-frequency radio waves were found to be problematic at night and in weather. By the end of the decade, use of high-frequency radio waves was explored and included the advent of high-frequency radar. In the 1940s, after 2 decades of development driven by mail carrier and passenger airline requirements, World War II injected urgency into the development of aircraft radio communication and navigation. Communication radios, despite their size, were essential on board aircraft. Figure 112. Very high frequencies were developed for communication and navigational purposes. Installation of the first instrument landing systems for blind landings began mid-decade, and by the end of the decade, the Very High-Frequency Omnidirectional Range VOR navigational network was instituted. It was also in the 1940s that the first transistor was developed, paving the way for modern, solid-state electronics. Civilian air transportation increased over the ensuing decades. Communication and navigation equipment was refined. Solid-state radio development, especially in the 1960s, produced a wide range of small, rugged radio and navigational equipment for aircraft. The space program began and added a higher level of communication and navigational necessity. Communication satellites were also launched. The Cold War military buildup caused developments in guidance and navigation and gave birth to the concept of using satellites for positioning. In the 1970s, concept validation of satellite navigation was introduced for the military, and Block Wine Global Positioning System (GPS) satellites were launched well into the 1980s. Back on Earth, the Long Range Navigation System (LORAN) was constructed. Block 2 GPS satellites were commissioned in the mid-80s, and GPS became operational in 1990, with the full 24-satellite system operational in 1994. In the new millennium, the Federal Aviation Administration, FAA, assessed the National Airspace System, NAS, and traffic projections for the future. Gridlock is predicted by 2022. Therefore, a complete overhaul of the NAS, including communication and navigational systems, has been developed and undertaken. The program is called NextGen. It uses the latest technologies to provide a more efficient and effective system of air traffic management. Heavily reliant on global satellite positioning of aircraft in flight and on the ground, NextGen combines GPS technology with automatic dependent surveillance broadcast technology, ADS-B, for traffic separation. A large increase in air system capacity is the planned result. Overhauled ground facilities accompany the technology upgrades mandated for aircraft. NextGen implementation has started and is currently scheduled through the year 2025. For the past few decades, avionics development has increased at a faster pace than that of airframe and power plant development. This is likely to continue in the near future. Improvements to solid-state electronics in the form of micro and nanotechnologies continue to this day. Trends are toward lighter, smaller devices with remarkable capability and reliability. Integration of the wide range of communication and navigational aids is a focus. Fundamentals of electronics. Analog versus digital electronics. Electronic devices represent and manipulate real-world phenomenon through the use of electrical signals. Electronic circuits are designed to perform a wide array of manipulations. Analog representations are continuous. Some aspect of an electric signal is modified proportionally to the real-world item that is being represented. For example, a microphone has electricity flowing through it that is altered when sound is applied. The type and strength of the modification to the electric signal is characteristic of the sound that is made into the microphone. The result is that sound, a real-world phenomenon, is represented electronically. It can then be moved, amplified, and reconverted from an electrical signal back into sound and broadcast from a speaker across the room or across the globe. Since the flow of electricity through the microphone is continuous, the sound continuously modifies the electric signal. On an oscilloscope, an analog signal is a continuous curve. Figure 113. An analog electric signal can be modified by changing the signal's amplitude, frequency, or phase. A digital electronic representation of a real-world event is discontinuous. The essential characteristics of the continuous event are captured as a series of discrete incremental values. Electronically, these representative samplings are successive chains of voltage and non-voltage signals. They can be transported and manipulated in electronic circuits. When the samples are sufficiently small and occur with high frequency, real-world phenomenon can be represented to appear continuous. Noise. A significant advantage of digital electronics over analog electronics is the control of noise. Noise is any alteration of the represented real-world phenomenon that is not intended or desired. Consider the operation of a microphone when understanding noise. A continuous analog voltage is modified by a voice signal that results in the continuous voltage varying in proportion to the volume and tone of the input sound. However, the voltage responds and modifies to any input. Thus, background sounds also modify the continuous voltage, as will electrostatic activity and circuitry imperfections. This alteration by phenomenon that are not the intended modifier is noise. During the processing of digitized data, there is little or no signal degradation. The real-world phenomenon is represented in a string of binary code. A series of ones and zeros are electronically created as a sequence of voltage or no voltage and carried through processing stages. It is relatively immune to outside alteration once established. If a signal is close to the set value of the voltage, it is considered to be that voltage. If the signal is close to zero, it is considered to be no voltage. Small variations or modifications from undesired phenomenon are ignored. Figure 114 illustrates an analog sine wave and a digital sine wave. Any unwanted voltage will modify the analog curve. The digital steps are not modified by small foreign inputs. There is either voltage or no voltage. All external events, including those that are not desired, called noise. Digital signals are a series of voltage or no voltage that represent a desired event. Electron control valves. Electron control valves are an essential part of an electronic circuit. Control of electron flow enables the circuit to produce the desired outcome. Early aircraft made use of vacuum tubes to control electron flow. Later, transistors replaced vacuum tubes. Semiconductors used in transistors and integrated circuits have enabled the solid-state digital electronics found in aircraft today. Vacuum tubes. Electron control valves found in the analog circuits of early aircraft electronics are constructed of vacuum tubes. Only antique aircraft retain radios with these devices due to their size and inability to withstand the harsh vibration and shock of the aircraft operating environment. However, they do function, and a description is included here as a foundation for the study of more modern electronic circuits and components. Diodes. A diode acts as a check valve in an alternating current, AC circuit. It allows current to flow during half of the AC cycle, but not the other half. In this manner, it creates a pulsating direct current, DC, with current that drops to zero in between pulses. A diode tube has two active electrodes, the cathode and the plate. It also contains a heater. All of this is housed in a vacuum environment inside the tube. Figure 115. The heater glows red hot while heating the cathode. The cathode is coated with a material whose electrons are excited by the heat. The excited electrons expand their orbit when heated. They move close enough to the plate, which is constructed around the cathode and heater arrangement, that they are attracted to the positively charged plate. When the AC current cycles, the plate becomes negatively charged and the excited cathode electrons do not flow to the plate. In a circuit, this causes a check valve effect that allows current to only flow in one direction, which is the definition of a diode. Figure 116. The various symbols used to depict diodes are shown in Figure 117. Triodes. A triode is an electron control valve containing three elements. It is often used to control a large amount of current with a smaller current flow. In addition to the cathode, plate, and heater present in the diode, a triode also contains a grid. The grid is composed of fine wire spiraled between the cathode and the plate, but closer to the cathode. Applying voltage to the grid can influence the cathode's electrons, which normally flow to the plate when the cathode is heated. Changes in the relatively small amount of current that flows through the grid can greatly impact the flow of electrons from the cathode to the plate. Figure 118. Figure 119 illustrates a triode in a simple circuit. A C voltage input is applied to the grid. A high-resistance resistor is used so that only minimum voltage passes through to the grid. As this small AC input voltage varies, the amount of DC output in the cathode plate circuit also varies. When the input signal is positive, the grid is positive. This aids in drawing electrons from the cathode to the plate. However, when the AC input signal cycles to negative, the grid becomes negatively charged, and flow from the cathode to the plate is cut off with the help of the negatively charged grid that repels the electrons on the cathode. Tetrodes. A tetrode vacuum tube electron control valve has four elements. In addition to the cathode, plate, and grid found in a triode, a tetrode also contains a screen grid. The cathode and plate of a vacuum tube electron control valve can act as a capacitor. At high frequencies, the capacitance is so low that feedback occurs. The output in the plate circuit feeds back into the control grid circuit. This causes an oscillation generating AC voltage that is unwanted. By placing a screen grid between the anode and the control grid windings, this feedback and the interelectrode capacitive effect of the anode and cathode are neutralized. Figure 1110. Figure 1111 illustrates a tetrode in a circuit. The screen grid is powered by positive DC voltage. The interelectrode capacitance is now between the screen grid and the plate. A capacitor is located between the screen grid and ground. A C feedback generated in the screen grid goes to ground and does not oscillate. This allows use of the tetrode at higher frequencies than a triode. Pentodes. The plate in a vacuum tube can have a secondary emission that must be controlled. When electrons flow from the cathode through the control grid and screen grid to the plate, they can arrive at such high velocity that some bounce off. Therefore, the tendency is for those electrons to be attracted to the positively charged screen grid. The screen grid is not capable of handling large amounts of current without burning up. To solve this problem, a third grid is constructed between the plate and the screen grid. Called a suppression grid, it is charged negatively so that secondary electron flow from the plate is repelled by the negative charge back toward the plate and is not allowed to reach the screen grid. The 5-element pentode is especially useful in high-power circuits where secondary emissions from the plate are high. Figure 1112. Solid-state devices. Solid-state devices began replacing vacuum tube electron control valves in the late 1950s. Their long life, reliability, and resilience in harsh environments make them ideal for use in avionics. Semiconductors. The key to solid-state electronic devices is the electrical behavior of semiconductors. To understand semiconductors, a review of what makes a material an insulator or a conductor follows. Then, an explanation for how materials of limited conductivity are constructed, and some of their many uses is explained. Semiconductor devices are the building blocks of modern electronics and avionics. An atom of any material has a characteristic number of electrons orbiting the nucleus of the atom. The arrangement of the electrons occurs in somewhat orderly orbits called rings or shells. The closest shell to the nucleus can only contain 2 electrons. If the atom has more than 2 electrons, they are found in the next orbital shell away from the nucleus. This second shell can only hold 8 electrons, if the atom element still has more electrons. However, when the fourth shell contains 8 electrons, the number of electrons in the third shell begins to increase again until a maximum of 18 is reached. Figure 1113. The outermost orbital shell of any atom's electrons is called the valence shell. The number of electrons in the valence shell determines the chemical properties of the material. When the valence shell has the maximum number of electrons, it is complete, and the electrons tend to be bound strongly to the nucleus. Materials with this characteristic are chemically stable. It takes a large amount of force to move the electrons in this situation from one atom valence shell to that of another. Since the movement of electrons is called electric current, substances with complete valence shells are known as good insulators because they resist the flow of electrons, electricity. Figure 1114. In atoms with an incomplete valence shell, that is, those without the maximum number of electrons in their valence shell, the electrons are bound less strongly to the nucleus. The material is chemically disposed to combine with other materials or other identical atoms to fill in the unstable valence configuration and bring the number of electrons in the valence shell to maximum. 2 or more substances may share the electrons in their valence shells and form a covalent bond. A covalent bond is the method by which atoms complete their valence shells by sharing valence electrons. Has more than 8 electrons, they orbit in a third shell farther out from the nucleus. This third shell is filled with 8 electrons, and then a fourth shell starts to fill if the electrons in incomplete valence shells may also move freely from valence shell to valence shell of different atoms or compounds. In this case, these are known as free electrons. As stated, the movement of electrons is known as electric. Zener diodes. Diodes can be designed with a Zener voltage. This is similar to avalanche flow. When reversed biased, only leakage current flows through the diode. However, as the voltage is increased, the Zener voltage is reached. The diode lets current flow freely through the diode in the direction in which it is normally blocked. The diode is constructed to be able to handle the Zener voltage and the resulting current, whereas avalanche voltage burns out a diode. A Zener diode can be used as means of dropping voltage or voltage regulation. It can be used to step down circuit voltage for a particular application, but only when certain input conditions exist. Zener diodes are constructed to handle a wide range of voltages. Figure 1125. Transistors. While diodes are very useful in electronic circuits, semiconductors can be used to construct true control valves known as transistors. A transistor is little more than a sandwich of N-type semiconductor material between two pieces of P-type semiconductor material or vice versa. However, a transistor exhibits some remarkable properties and is the building block of all things electronic. Figure 1126. As with any union of dissimilar types of semiconductor materials, the junctions of the P and N materials in a transistor have depletion areas that create potential hills for the flow of electrical charges. Like a vacuum tube triode, the transistor has 3 electrodes or terminals, one each for the 3 layers of semiconductor material. The emitter and the collector are on the outside of the sandwiched semiconductor material. The center material is known as the base. A change in a relatively small amount of voltage applied to the base of the transistor allows a relatively large amount of current to flow from the collector to the emitter. In this way, the transistor acts as a switch with a small input voltage controlling a large amount of current. If a transistor is put into a simple battery circuit, such as the one shown in figure 1127, voltage from the battery, EB, forces free electrons and holes toward the junction between the base and the emitter, just as it does in the junction of a semiconductor diode. The emitter-base depletion area becomes narrow as free electrons combine with the holes at the junction. Current IB solid arrows flows through the junction in the emitter-base battery circuit. At the same time, an emitter-collector circuit is constructed with a battery, EC, of much higher voltage in its circuit. Because of the narrow depletion area at the emitter-base junction, current IC is able to cross the collector-base junction, flow through emitter-base junction, and complete the collector-emitter battery circuit, hollow arrows. To some extent, varying the voltage to the base material can increase or decrease the current flow through the transistor as the emitter-base depletion area changes width in response to the base voltage. If base voltage is removed, the emitter-base depletion area becomes too wide and all current flow through the transistor ceases. Current in the transistor circuit illustrated has a relationship as follows: IE equals IB plus IC. It should be remembered that it is the voltage applied to the base that turns the collector-emitter transistor current on or off. Controlling a large amount of current flow with a small independent input voltage is very useful when building electronic circuits. Transistors are the building blocks from which all electronic devices are made, including Boolean gates that are used to create microprocessor chips. As production techniques have developed, the size of reliable transistors has shrunk. Now, hundreds of millions and even billions of transistors may be used to construct a single chip, such as the one that powers your computer and various avionic devices. Silicon-controlled rectifiers. Combination of semiconductor materials is not limited to a 2-type, 3-layer sandwich transistor. By creating a 4-layer sandwich of alternating types of semiconductor material, i.e. PNPN or NPNP, a slightly different semiconductor diode is created. As is the case in a 2-layer diode, circuit current is either blocked or permitted to flow through the diode in a single direction. Within a 4-layer diode, sometimes known as a Shockley diode, there are 3 junctions. The behavior of the junctions and the entire 4-layer diode can be understood by considering it to be 2 interconnected 3-layer transistors. Figure 1128. Transistor behavior includes no current flow until the base material receives an applied voltage to narrow the depletion area at the base emitter junction. The base materials in the 4-layer diode transistor model receive charge from the other transistor's collector. With no other means of reducing any of the depletion areas at the junctions, it appears that current does not flow in either direction in this device. However, if a large voltage is applied to forward bias, the anode or cathode, at some point the ability to block flow breaks down. current flows through whichever transistor is charged. Collector current then charges the base of the other transistor, and current flows through the entire device. Some caveats are necessary with this explanation. The transistors that comprise this four-layer diode must be constructed of material similar to that described in a Zener diode. That is, it must be able to endure the current flow without burning out. In this case, the voltage that causes the diode to conduct is known as breakover voltage rather than breakdown voltage. Additionally, this diode has the unique characteristic of allowing current flow to continue until the applied voltage is reduced significantly, in most cases, until it is reduced to zero. In AC circuits, this would occur when the AC cycles. While the four-layer Shockley diode is useful as a switching device, a slight modification to its design creates a silicon-controlled rectifier, SCR. To construct a SCR, an additional terminal known as a gate is added. It provides more control and utility. In the four-layer semiconductor construction, there are always two junctions forward-biased and one junction reversed-biased. The added terminal allows the momentary application of voltage to the reversed-biased junction. All three junctions then become forward-biased, and current at the anode flows through the device. Once voltage is applied to the gate, the SCR becomes latched or locked on. Current continues to flow through it until the level drops off significantly, usually to zero. Then another applied voltage through the gate is needed to reactivate the current flow. Figures 1129 and 1130. SCRs are often used in high-voltage situations, such as power switching, phase controls, battery chargers, and inverter circuits. They can be used to produce variable DC voltages for motors and are found in welding power supplies. Often, lighting dimmer systems use SCRs to reduce the average voltage applied to the lights by only allowing current flow during part of the AC cycle. This is controlled by controlling the pulses to the SCR gate and eliminating the massive heat. Triacs. SCRs are limited to allowing current flow in one direction only. In AC circuitry, this means only half of the voltage cycle can be used and controlled. To access the voltage in the reverse cycle from an AC power source, a triac can be used. A triac is also a four-layer semiconductor device. It differs from an SCR in that it allows current flow in both directions. A triac has a gate that works the same way as in a SCR. However, a positive or negative pulse to the gate triggers current flow in a triac. The pulse polarity determines the direction of the current flow through the device. Figure 1132 illustrates a triac and shows a triac in a simple circuit. It can be triggered with a pulse of either polarity and remains latched until the voltage declines, such as when the AC cycles. Then, it needs to be triggered again. In many ways, the triac acts as though it is two SCRs connected side by side, only in opposite directions. Like an SCR, the timing of gate pulses determines the amount of the total voltage that is allowed to pass. The output waveform, if triggered at 90 degrees, is shown in figure 1132. Because a triac allows current to flow in both directions, the reverse cycle of AC voltage can also be used and controlled. When used in actual circuits, triacs do not always maintain the same phase firing point in reverse as they do when fired with a positive pulse. This problem can be regulated somewhat through the use of a capacitor and a diac in the gate circuit. However, as a result, where precise control is required, two SCRs in reverse of each other are often used instead of the triac. Triacs do perform well in lower voltage circuits. Figure 1133 illustrates the semiconductor layering in a triac. Note, the four layers of N and P-type materials are not uniform as they were in previously described semiconductor devices. Nonetheless, Gate pulses affect the depletion areas at the junctions of the materials, in the same way allowing current to flow when the areas are narrowed. Unijunction transistors, UJT. The behavior of semiconductor materials is exploited through the construction of numerous transistor devices containing various configurations of N-type and P-type materials. The physical arrangement of the materials in relation to each other yields devices with unique behaviors and applications. The transistors described above having two junctions of P-type and N-type materials, PN, are known as bipolar junction transistors. Other more simple transistors can be fashioned with only one junction of the PN semiconductor materials. These are known as unijunction transistors, UJT. Figure 1134. The UJT contains one base semiconductor material and a different type of emitter semiconductor material. There is no collector material. One electrode is attached to the emitter, and two electrodes are attached to the base material at opposite ends. These are known as base 1, B1, and base 2, B2. The electrode configuration makes the UJT appear physically the same as a bipolar junction transistor. However, there is only one PN junction in the UJT, and it behaves differently. The base material of a UJT behaves like a resistor between the electrodes. With B2 positive with respect to B1, voltage gradually drops as it flows through the base. Figure 1135. By placing the emitter at a precise location along the base material gradient, the amount of voltage needed to be applied to the emitter electrode to forward bias, the UJT base emitter junction, is determined. When the applied emitter voltage. Field effect transistors, FET. As shown in the TRIAC and the UJT, creative arrangement of semiconductor material types can yield devices with a variety of characteristics. The field effect transistor, FET, is another such device which is commonly used in electronic circuits. Its N and P-type material configuration is shown in figure 1136. A FET contains only one junction of the two types of semiconductor material. It is located at the gate where it contacts the main current carrying portion of the device. Because of this, when an FET has a PN junction, it is known as a junction field effect transistor, JFET. All FETs operate by expanding and contracting the depletion area at the junction of the semiconductor materials. One of the materials in a FET or JFET is called the channel. It is usually the substrate through which the current needing to be controlled flows from a source terminal to a drain terminal. The other type of material intrudes into the channel and acts as the gate. The polarity and amount of voltage applied to the gate can widen or narrow the channel due to expansion or shrinking of the depletion area at the junction of the semiconductors. This increases or decreases the amount of current that can flow through the channel. Enough reversed biased voltage can be applied to the gate to prevent the flow of current through the channel. This allows the FET to act as a switch. It can also be used as a voltage-controlled resistance. FETs are easier to manufacture than bipolar transistors and have the advantage of staying on once current flow begins without continuous gate voltage applied. They have higher impedance than bipolar transistors and operate cooler. This makes their use ideal for integrated circuits where millions of FETs may be in use on the same chip. FETs come in N-channel and P-channel varieties, metal oxide semiconductor, field effect transistors, MOSFETs, and complementary metal oxide semiconductor, CMOS. The basic FET has been modified in numerous ways and continues to be at the center of faster and smaller electronic component development. A version of the FET widely used is the metal oxide semiconductor field effect transistor, MOSFET. The MOSFET uses a metal gate with a thin insulating material between the gate and the semiconductor material. This essentially creates a capacitor at the gate and eliminates current leakage in this area. Modern versions of the MOSFET have a silicon dioxide insulating layer, and many have polycrystalline silicon gates rather than metal, but the MOSFET name remains and the basic behavioral characteristic are the same. Figure 1137. As with FETs, MOSFETs come with N-channels or channels. They can also be constructed as depletion mode or enhancement mode devices. This is analogous to a switch being normally open or normally closed. Depletion mode. MOSFETs have an open channel that is restricted or closed when voltage is applied to the gate, i.e., normally open. Enhancement mode. MOSFETs allow no current to flow at zero bias, but create a channel for current flow when voltage is applied to the gate, normally closed. No voltage is used when the MOSFETs are at zero bias. Millions of enhancement mode MOSFETs are used in the construction of integrated circuits. They are installed in complementary pairs such that when one is open, the other is closed. This basic design is known as complementary MOSFET, CMOS, which is the basis for integrated circuit design in nearly all modern electronics. Through the use of these transistors, digital logic gates can be formed, and digital circuitry is constructed. Other more specialized FETs exist. Some of their unique characteristics are owed to design alterations and others to material variations. The transistor devices discussed above use silicon-based semiconductors, but the use of other semiconductor materials can yield variations in performance. Metal semiconductor FETs, MESFETs for example, are often used in microwave applications. They have a combined metal and semiconductor material at the gate and are typically made from gallium arsenide or indium phosphide. MESFETs are used for their quickness when starting and stopping current flows, especially in opposite directions. High electron mobility transistors, HEMT, and pseudomorphic high electron mobility transistors, PHEMT, are also constructed from gallium arsenide semiconductor material and are used for high-frequency applications. Photodiodes and phototransistors. Light contains electromagnetic energy that is carried by photons. The amount of energy depends on the frequency of light of the photon. This energy can be very useful in the operation of electronic devices, since all semiconductors are affected by light energy. When a photon strikes a semiconductor atom, it raises the energy level above what is, figure 1136. The basic structure of a field effect transistor, and it's needed to hold its electrons in orbit. The extra energy frees an electronic symbol, electron enabling it to flow as current, the vacated position. Light-emitting diodes. Light-emitting diodes, LEDs, have become so commonly used in electronics that their importance may tend to be overlooked. Numerous avionics displays and indicators use LEDs for indicator lights, digital readouts, and backlighting of liquid crystal display LCD screens. LEDs are simple and reliable. They are constructed of semiconductor material. When a free electron from a semiconductor drops into a semiconductor hole, energy is given off. This is true in all semiconductor materials. However, the energy released when this happens in certain materials is in the frequency range of visible light. Figure 1141 is a table that illustrates common LED colors and the semiconductor material that is used in the construction of the diode. Note: when the diode is reversed biased, no light is given off. When the diode is forward biased, the energy given off is visible in the color characteristic for the material being used. Figure 1142 illustrates the anatomy of a single LED, the symbol of an LED, and a graphic depiction of the LED process. Basic analog circuits. The solid-state semiconductor devices described in the previous section of this chapter can be found in both analog and digital electronic circuits. As digital electronics evolve, analog circuitry is being replaced. However, many aircraft still make use of analog electronics in radio and navigation equipment, as well as in other aircraft systems. A brief look at some of the basic analog circuits follows. Rectifiers. Rectifier circuits change AC voltage into DC voltage and are one of the most commonly used type of circuits in aircraft electronics. Figure 1143, the resulting DC waveform. Output is also shown. The circuit has a single semiconductor diode and a load resistor. When the AC voltage cycles below zero, the diode shuts off and does not allow current flow until the AC cycles through zero voltage again. The result is pronounced pulsating DC. While this can be useful, half of the original AC voltage is not being used. A full-wave rectifier creates pulsating DC from AC while using the full AC cycle. One way to do this is to tap the secondary coil at its midpoint and construct two circuits with the load resistor and a diode in each circuit. Figure 1144. The diodes are arranged so that when current is flowing through one, the other blocks current. When the AC cycles so the top of the secondary coil of the transformer is positive, current flows from ground through the load resistor, VRL, diode 1, and the upper half of the coil. Current cannot flow through diode 2 because it is blocked. Figure 1144A. As the AC cycles through zero, the polarity of the secondary coil changes. Figure 1144B. Current then flows from ground through the load resistor, diode 2, and the bottom half of the secondary coil. Current flow through diode 1 is blocked. This arrangement yields positive DC from cycling AC with no wasted current. Another way to construct a full-wave rectifier uses 4 semiconductor diodes in a bridge circuit. Because the secondary coil of the transformer is not tapped at the center, the resultant DC voltage output is twice that of the 2-diode full-wave rectifier. Figure 1145. During the first half of the AC cycle, the bottom of the secondary coil is negative. Current flows from it through diode D1, then through the load resistor, and through diode D2 on its way back to the top of the secondary coil. When the AC reverses its cycle, the polarity of the secondary coil changes. Current flows from the top of the coil through diode D3, then through the load resistor, and through diode D4 on its way back to the bottom of the secondary coil. The output waveform reflects the higher voltage achieved by rectifying the full AC cycle through the entire length of the secondary coil. Use and rectification of three-phase AC is also possible on aircraft with a specific benefit. The output DC is very smooth and does not drop to zero. A 6-diode circuit is built to rectify. Amplifiers. An amplifier is a circuit that changes the amplitude of an electric signal. This is done through the use of transistors. As mentioned, a transistor that is forward biased at the base emitter junction and reversed biased at the collector base junction is turned on. It can conduct current from the collector to the emitter. Because a small signal at the base can cause a large current to flow from collector to emitter, a transistor in itself can be said to be an amplifier. However, a transistor properly wired into a circuit with resistors, power sources, and other electronic components, such as capacitors, can precisely control more than signal amplitude. Phase and impedance can also be manipulated. Since the typical bipolar junction transistor requires a based circuit and a collector-emitter circuit, there should be 4 terminals, 2 for each circuit. However, the transistor only has 3 terminals, i.e., the base, the collector, and the emitter. Therefore, one of the terminals must be common to both transistor circuits. The selection of the common terminal affects the output of the amplifier. The three basic amplifier types, named for which terminal of the transistor is the common terminal to both transistor circuits, include common emitter amplifier, common collector amplifier, common base amplifier, common emitter amplifier. The common emitter amplifier controls the amplitude of an electric signal and inverts the phase of the input signal. Figure 1147 illustrates a common emitter amplifier for AC using a NPN transistor and its output signal graph. Common emitter circuits are characterized by high current gain and a 180-degree voltage phase shift from input to output. It is for the amplification of a microphone signal to drive a speaker. As always, adequate voltage of the correct polarity to the base puts the transistor in the active mode or turns it on. Then, as the base input current fluctuates, the current through the transistor fluctuates proportionally. However, AC cycles through positive and negative polarity. Every 180 degrees, the transistor shuts off because the polarity to the base emitter junction of the transistor is not correct to forward bias the junction. To keep the transistor on, a DC biasing voltage of the correct polarity, shown as a 2.3 volts V battery, is placed in series with the input signal in the base circuit to hold the transistor in the active mode as the AC polarity changes. This way, the transistor stays in the active mode to amplify an entire AC signal. Transistors are rated by ratio of the collector current to S. S is I, the manufacturer of the unit, and cannot be changed. A SAZADIC. Cis collector emitter circuit than the base input signal. This current in figure 1147 is provided from the 15-volt battery, V1. So the amplitude of amplification is a factor of the beta of the transistor and any inline resistors used in the circuits. The fluctuations of the output signal, however, are entirely controlled by the fluctuations of current input to the transistor base. If measurements of input and output voltages are made, it is shown that as the input voltage increases, the output voltage decreases. This accounts for the inverted phase produced by a common emitter circuit. Figure 1147. Common collector amplifier. Another basic type of amplifier circuit is the common collector amplifier. Common collector circuits are characterized by high current gain, but virtually no voltage gain. The input circuit and the load circuit in this amplifier share the collector terminal of the transistor used. Because the load is in series with the emitter, both the input current and output current run through it. This causes a directly proportional relationship between the input and the output. The current gain in this circuit configuration is high. A small amount of input current can control a large amount of current to flow from the collector to the emitter. A common collector amplifier circuit is illustrated in figure 1148. The base current needs to flow through the PN junction of the transistor, which has about a 0.7 V threshold to be turned on. The output current of the amplifier is the beta value of the transistor plus 1. During AC amplification, the common collector amplifier has the same problem that exists in the common emitter amplifier. The transistor must stay on or in the active mode, regardless of input signal polarity. When the AC cycles through zero, the transistor turns off because the minimum amount of current to forward bias the transistor is not available. The addition of a DC biasing source battery in series with the AC signal in the input circuit keeps the transistor in the active mode throughout the full AC cycle. Figure 1149. A common collector amplifier can also be built with a PNP transistor. Figure 1150. It has the same characteristics as the NPN common collector amplifier shown in Figure 1150. When arranged with a high resistance in the input circuit and a small resistance in the load circuit, the common collector amplifier can be used to step down the impedance of a signal. Figure 1151. Common base amplifier. A third type of amplifier circuit using a bipolar transistor is the common base amplifier. In this circuit, the shared transistor terminal is the base terminal. Figure 1152. This causes a unique situation in which the base current is actually larger than the collector or emitter current. As such, the common base amplifier does not boost current as the other amplifiers do. It attenuates current but causes a high gain in voltage. A very small fluctuation in base voltage in the input circuit causes a large variation in output voltage. The effect on the circuit output is direct, so the output voltage phase is the same as the input signal, but much greater in amplitude. As with the other amplifier circuits, when amplifying an AC signal with a common base amplifier circuit, the input signal to the base must include a DC source to forward bias the transistor's base emitter junction. This allows current to flow from the collector to the emitter during both cycles of the AC. A circuit for AC amplification is illustrated in Figure 1153 with a graph of the output voltage showing the large increase produced. The common base amplifier is limited in its use since it does not increase current flow. This makes it the least used configuration. However, it is used in radio frequency amplification because of the low input Z. Figure 1154 summarizes the characteristics of the bipolar amplifier circuits discussed above. Note: there are many variations in circuit design. JFETs and MOSFETs are also used in amplifier circuits, usually in small signal amplifiers due to their low noise outputs. Oscillator circuits. Oscillators function to make AC from DC. They can produce various waveforms as required by electronic circuits. There are many different types of oscillators and oscillator circuits. Some of the most common types are discussed below. A sine wave is produced by generators when a conductor is rotated in a uniform magnetic field. The typical AC sine wave is characterized by a gradual build-up and decline of voltage in one direction, followed by a similar smooth build-up to peak voltage and decline to zero again in the opposite direction. The value of the voltage at any given time in the cycle can be calculated by taking the peak voltage and. A square wave is produced when there is a flow of electrons for a set period that stops for a set amount of time and then repeats. In DC current, this is simply pulsing DC. Figure 1156. This same waveform can be of opposite polarities when passed through a transformer to produce AC. Certain oscillators produce square waves. An oscillator known as a relaxation oscillator produces another kind of wave form, a sawtooth wave. A slow rise from zero to peak voltage is followed by a rapid drop-off of voltage back to almost zero. Then it repeats. Figure 1157. In the circuit, a capacitor slowly charges through a resistor. A neon bulb is wired across the capacitor. When its ignition voltage is reached, the bulb conducts. This short-circuits the charged capacitor, which causes the voltage to drop to nearly zero and the bulb goes out. Then, the voltage rises again as the cycle repeats. Electronic oscillation. Oscillation in electronic circuits is accomplished by combining a transistor and a tank circuit. A tank circuit is comprised of a capacitor and coil parallel to each other. Figure 1158. When attached to a power source by closing switch A, the capacitor charges to a voltage equal to the battery voltage. It stays charged, even when the circuit to the battery is open. Switch in position B. When the switch is put in position C, the capacitor and coil are in a closed circuit. The capacitor discharges through the coil. While receiving the energy from the capacitor, the coil stores it by building up an electromagnetic field. When the capacitor is fully discharged, the coil stops conducting. The magnetic field collapses, which induces current flow. The current charges the opposite plate of the capacitor. When completely charged, the capacitor discharges into the coil again. The magnetic field builds again and stops when the capacitor is fully discharged. The magnetic field collapses again, which induces current that charges the original plate of the capacitor, and the cycle repeats. This oscillation of charging and discharging the capacitor through the coil would continue indefinitely if a circuit could be built with no resistance. This is not possible. However, a circuit can be built using a transistor that restores losses due to resistance. There are various ways to accomplish this. The Hartley oscillator circuit in Figure 1159 is one. The circuit can oscillate indefinitely as long as it is connected to power. When the switch is closed, current begins to flow in the oscillator circuit. The transistor base is supplied with biasing current through the voltage divider RA and RB. This allows current to flow through the transistor from the collector to the emitter through RE and through the lower portion of the center-tapped coil that is labeled L1. The current increasing through this coil builds a magnetic field that induces current in the upper half of the coil labeled L2. The current from L2 charges capacitor C2, which increases the forward bias of the transistor. This allows an increasing flow of current through the transistor RE and L1 until the transistor is saturated and capacitor C1 is fully charged. Without force to add electrons to capacitor C1, it discharges and begins the oscillation in the tank circuit described in the previous section. As C1 becomes fully charged, current to charge C2 reduces and C2 also discharges. This adds the energy needed to the tank circuit to compensate for resistance losses. As C2 is discharging, it reduces forward biasing, and eventually the transistor becomes reversed biased and cuts off. When the opposite plate of capacitor C1 is fully charged, it discharges, and the oscillation is in progress. The transistor base becomes forward biased again, allowing for current flow through the resistor RE, coil L1, etc. The frequency of the AC oscillating in the Hartley oscillator circuit depends on the inductance and capacitance values of the components used. Use of a crystal in an oscillator circuit can control the frequency more accurately. A crystal vibrates at a single consistent frequency. When flexed, a small pulse of current is produced through the piezoelectric effect. Placed in the feedback loop, the pulses from the crystal control the frequency of the oscillator circuit. The tank circuit component values are tuned to match the frequency of the crystal. Oscillation is maintained as long as power is supplied. Figure 1160. Other types of oscillator circuits used in electronics and computers have two transistors that alternate being in the active mode. They are called multivibrators. The choice of oscillator in an electronic device depends on the exact type of manipulation of electricity required to permit the device to function as desired. Digital electronics. The above discussion of semiconductors, semiconductor devices, and circuitry is only an introduction to the electronics found in communications and navigation avionics. In-depth maintenance of the interior electronics on most avionics devices is performed only by certified repair stations and trained avionics technicians. The airframe technician is responsible for installation, maintenance, inspection, and proper performance of avionics in the aircraft. Modern aircraft increasingly employs digital electronics in avionics rather than analog electronics. Transistors are used in digital electronics to construct circuits that act as digital logic gates. The purpose and task of a device is achieved by manipulating electric signals through the logic gates. Thousands and even millions of tiny transistors can be placed on a chip to create the digital logic landscape through which a component's signals are processed. Digital building blocks. Digital logic is based on the binary number system. There are two conditions that may exist, 1 or 0. In a digital circuit, these are equivalent to voltage or no voltage. Within the binary system, these two conditions are called logic 1 and logic 0. Using just these two conditions, gates can be constructed to manipulate information. There are a handful of common logic gates that are used. By combining any number of these tiny solid-state gates, significant memorization, manipulation, and calculation of information can be performed. The NOT gate. The NOT gate is the simplest of all gates. If the input to the gate is logic 1, then the output is not logic 1. This means that it is logic 0, since there are only two conditions in the binary world. In an electronic circuit, a NOT gate would invert the input signal. In other words, if there was voltage at the input to the gate, there would be no output voltage. The gate can be constructed with transistors and resistors to yield this electrical logic every time. The gate or circuit would also have to invert an input of logic 0 into an output of logic 1. To understand logic gates, truth tables are often used. A truth table gives all of the possibilities in binary terms for each gate containing a characteristic logic function. For example, a truth table for a NOT gate is illustrated in figure 1161. Any input, A, is not present at the output, B. This is simple, but it defines this logic situation. A tiny NOT gate circuit can be built using transistors that produce these results. In other words, a circuit can be built such that if voltage arrives at the gate, no voltage is output or vice versa. When using transistors to build logic gates, the primary concern is to operate them within the circuits, so the transistors are either off, not conducting, or fully on, saturated. In this manner, reliable logic functions can be performed. The variable voltage and current situations present during the active mode of the transistor are of less importance. Figure 1162 illustrates an electronic circuit diagram that performs the logic NOT gate function. Any input, either a no voltage or voltage condition, yields the opposite output. This gate is built with bipolar junction transistors, resistors, and a few diodes. Other designs exist that may have different components. When examining and discussing digital electronic circuits, the electronic circuit design of a gate is usually not presented. The symbol for the logic gate is most often used. Figure 1161. The technician can then concentrate on the configuration of the logic gates in relation to each other. A brief discussion of the other logic gates, their symbols and truth tables follow. Buffer gate. Another logic gate with only one input and one output is the buffer. It is a gate with the same output as the input. While this may seem redundant or useless, an amplifier may be considered a buffer in a digital circuit, because if there is voltage present at the input, there is an output voltage. If there is no voltage at the input, there is no output voltage. When used as an amplifier, the buffer can change the values of a signal. This is often done to stabilize a weak or varying signal. All gates are amplifiers subject to output fluctuations. The buffer steadies the output of the upstream device while maintaining its basic characteristic. Another application of a buffer that is two NOT gates is to use it to isolate a portion of a circuit. Figure 1163. Digital aircraft systems. Digital aircraft systems are the present and future of aviation. From communication and navigation to engine and flight controls, increased proliferation of digital technology increases reliability and performance. Processing, storing and transferring vital information for the operation of an aircraft in digital form provides a usable common language for monitoring, control and safety. Integration of information from different systems is simplified. Self-monitoring, built-in test equipment, BITE, and air-to-ground data links increase maintenance efficiency. Digital bus networking allows aircraft system computers to interact for a coordinated, comprehensive approach to flight operations. Digital data displays. Modern digital data displays are the most visible features of digital aircraft systems. They extend the functional advantages of state-of-the-art digital communication and navigation avionics and other digital aircraft systems via the use of an enhanced interface with the pilot. The result is an increase in situational awareness and overall safety of flight. Digital data displays are the glass of the glass flight deck. They expand the amount, clarity, and proximity of the information presented to the pilot. Figure 1170. Many digital data displays are available from numerous manufacturers as original equipment in new aircraft, or as retrofit components or complete retrofit systems for older aircraft. Approval for retrofit displays is usually accomplished through Supplementary Type Certificate, STC, awarded to the equipment manufacturer. Early digital displays presented scale indication in digital or integer format readouts. Today's digital data displays are analogous to computer screen presentations. Numerous aircraft and flight instrument readouts and symbolic presentations are combined with communication and navigational information on multifunctional displays, MFD. Often a display has a main function with potential to back up another display should it fail. Names such as primary flight display, PFD, secondary flight display, navigational display, ND, etc. are often used to describe a display by its primary use. The hardware composition of the displays is essentially the same. Avionics components and computers combine to provide the different information portrayed on the displays. Controls on the instrument panel or on the display unit itself are used for selection. Some screens have limited display capability because they are not part of a totally integrated system. However, they are extremely powerful electronic units with wide capability. Figure 1171. The basis of the information displayed on what is known as a PFD is usually an electronic flight instrument system, EFIS, like representation of the aircraft attitude indicator in the upper half of the display, and an electronic horizontal situation indicator display on the lower half. Numerous ancillary readouts are integrated or surround the electronic attitude indicator and the horizontal situation indicator, HSI. On full glass flight deck PFDs, all of the basic T instrument indications are presented and much more, such as communication and navigation information, weather data, terrain features, and approach information. Data displays for engine parameters, hydraulics, fuel, and other airframe systems are often displayed on the secondary flight display or on an independent display made for this purpose. Figure 1172. As with other avionics components, repair and maintenance of the internal components of digital data displays is reserved for licensed repair stations only. Digital tuners and audio panels. Numerous communication and navigation devices are described in the following sections of this chapter. Many of these use radio waves and must be tuned to a desired frequency for operation. As a flight progresses, retuning and changing from one piece of equipment to another can occur frequently. An audio panel or digital tuner consolidates various communication and navigation radio selection controls into a single unit. The pilot can select and use, or radio communication. Much of aviation communication and navigation is accomplished through the use of radio waves. Communication by radio was the first use of radio frequency transmissions in aviation. Radio waves. A radio wave is invisible to the human eye. It is electromagnetic in nature and part of the electronic spectrum of wave activity that includes gamma rays, X-rays, ultraviolet rays, infrared waves, and visible light rays, as well all radio waves. Figure 1174. The atmosphere is filled with these waves. Each wave occurs at a specific frequency and has a corresponding wavelength. The relationship between frequency and wavelength is inversely proportional. A high-frequency wave has a short wavelength, and a low-frequency wave has a long wavelength. In aviation, a variety of radio waves are used for communication. Figure 1175 illustrates the radio spectrum that includes the range of common aviation radio frequencies and their applications. Note: a wide range of frequencies are used from low frequency, LF, at 100 kHz, 100,000 cycles per second, to super high frequency, SHF, at nearly 10 GHz, 10 billion cycles per second. The Federal Communications Commission, FCC, controls the assignment of frequency usage. A C-power of a particular frequency has a characteristic length of conductor that is resonant at that frequency. This length is the wavelength of the frequency that can be seen on an oscilloscope. Fractions of the wavelength also resonate, especially half of a wavelength, which is the same as half of the AC sine wave or cycle. The frequency of an AC signal is the number of times the AC cycles every second. AC applied to the center of a radio antenna. A conductor half the wavelength of the AC frequency travels the length of the antenna, collapses, and travels the length of the antenna in the opposite direction. The number of times it does this every second is known as the radio wave signal frequency, or radio frequency, as shown in figure 1175. As the current flows through the antenna, corresponding electromagnetic and electric fields build, collapse, build in the opposite direction, and collapse again. Figure 1176. To transmit radio waves, an AC generator is placed at the midpoint of an antenna. As AC current builds and collapses in the antenna, a magnetic field also builds and collapses around it. An electric field also builds and subsides as the voltage shifts from one end of the antenna to the other. Both fields, the magnetic and the electric, fluctuate around the antenna at the same time. The antenna is half the wavelength of the AC signal received from the generator. At any one point along the antenna, voltage and current vary inversely to each other. Because of the speed of the AC, the electromagnetic fields and electric fields created around the antenna do not have time to completely collapse as the AC cycles. Each new current flow creates new fields around the antenna that force the not totally collapsed fields from the previous AC cycle out into space. These are the radio waves. The process is continuous as long as AC is applied to the antenna. Thus, steady radio waves of a frequency determined by the input AC frequency propagate out into space. Radio waves are directional and propagate out into space at 186,000 miles per second. The distance they travel depends on the frequency and the amplification of the signal AC sent to the antenna. The electric field component and the electromagnetic field component are oriented at 90 degrees to each other and at 90 degrees to the direction that the wave is traveling. Figure 1177. Types of radio waves. Radio waves of different frequencies have unique characteristics as they propagate through the atmosphere. Very low frequency, VLF, LF, and medium frequency, MF, waves have relatively long wavelengths and utilize correspondingly long antennas. Radio waves produced at these frequencies, ranging from 3 kHz to 3 MHz, are known as ground waves or surface waves. This is because they follow the curvature of the Earth as they travel from the broadcast antenna to the receiving antenna. Ground waves are particularly useful for long-distance transmissions. Automatic direction finders, ADF, and LORAN navigational aids use these frequencies. Figure 1178. High frequency, HF. Radio waves travel in a straight line and do not curve to follow the Earth's surface. This would limit transmissions from the broadcast antenna to receiving antennas only in the line of sight of the broadcast antenna, except for a unique characteristic. HF radio waves bounce off of the ionosphere layer of the atmosphere. This refraction, amplitude modulation, AM. A radio wave can be altered to carry useful information by modulating the amplitude of the wave. A DC signal, for example from a microphone, is amplified and then superimposed over the AC carrier wave signal. As the varying DC information signal is amplified, the amplifier output current varies proportionally. The oscillator that creates the carrier wave does so with this varying current. The oscillator frequency output is consistent because it is built into the oscillator circuit, but the amplitude of the oscillator output varies in relation to the fluctuating current input. Figure 1179. When the modulated carrier wave strikes the receiving antenna, voltage is generated that is the same as that which was applied to the transmitter antenna. However, the signal is weaker. It is amplified so that it can be demodulated. Demodulation is the process of removing the original information signal from the carrier wave. Electronic circuits containing capacitors, inductors, diodes, filters, etc. remove all but the desired information signal identical to the original input signal. Then the information signal is typically amplified again to drive speakers or other output devices. Figure 1180. AM has limited fidelity. Atmospheric noises or static alter the amplitude of a carrier wave, making it difficult to separate the intended amplitude modulation caused by the information signal and that which is caused by static. It is used in aircraft VHF communication radios. Frequency modulation, FM. Frequency modulation, FM, is widely considered superior to AM for carrying and deciphering information on radio waves. A carrier wave modulated by FM retains its constant amplitude. However, the information signal alters the Figure 11-76. Radio waves are produced by applying an AC signal to an antenna. This creates a magnetic and electric field around the antenna. They build and collapse as the AC cycles. The speed at which the AC cycles does not allow the fields to completely collapse before the next fields build. The collapsing fields are then forced out into space as radio waves. Single sideband, SSB. When two AC signals are mixed together, such as when a carrier wave is modulated by an information signal, three main frequencies result: original carrier wave frequency, carrier wave frequency plus the modulating frequency, and transmitters. A transmitter consists of a precise oscillating circuit or oscillator that creates an AC carrier wave frequency. This is combined with amplification circuits or amplifiers. The distance a carrier wave travels is directly related to the amplification of the signal sent to the antenna. Other circuits are used in a transmitter to accept the input information signal and process it for loading onto the carrier wave. Modulator circuits modify the carrier wave with the processed information signal. Essentially, this is all there is to a radio transmitter. Note: modern transmitters are highly refined devices with extremely precise frequency oscillation and modulation. The circuitry for controlling, filtering, amplifying, modulating, and oscillating electronic signals can be complex. A transmitter prepares and sends signals to an antenna that, in the process described above, radiates the waves out into the atmosphere. A transmitter with multiple channel frequency capability contains tuning circuitry that enables the user to select the frequency upon which to broadcast. This adjusts the oscillator output to the precise frequency desired. It is the oscillator frequency that is being tuned. Figure 1184. As shown in Figure 1184, most radio transmitters generate a stable oscillating frequency and then use a frequency multiplier to raise the AC to the transmitting frequency. This allows oscillation to occur at frequencies that are controllable and within the physical working limits of the crystal in crystal-controlled oscillators. Receivers. Antennas are simply conductors of lengths proportional to the wavelength of the oscillated frequency put out by the transmitter. An antenna captures the desired carrier wave as well as many other radio waves that are present in the atmosphere. A receiver is needed to isolate the desired carrier wave with its information. The receiver also has circuitry to separate the information signal from the carrier wave. It prepares it for output to a device, such as speakers or a display screen. The output is the information signal originally introduced into the transmitter. A common receiver is the super-heterodyne receiver. As with any receiver, it must amplify the desired radio frequency captured by the antenna since it is weak from traveling through the atmosphere. An oscillator in the receiver is used to compare and select the desired frequency out of all of the frequencies picked up by the antenna. The undesired frequencies are sent to ground. A local oscillator in the receiver produces a frequency that is different than the radio frequency of the carrier wave. These two frequencies are mixed in the mixer. 4 frequencies result from this mixing. They are the radio frequency, the local oscillator frequency, and the sum and difference of these two frequencies. The sum and difference frequencies contain the information signal. The frequency that is the difference between the local oscillator frequency and the radio frequency carrier wave frequency is used during the remaining processing. In VHF aircraft communication radios, this frequency is 10.8 MHz. Called the intermediate frequency, it is amplified before it is sent to the detector. The detector or demodulator is where the information signal is separated from the carrier wave portion of the signal. In AM, since both sidebands contain the useful information, the signal is rectified, leaving just one sideband with a weak version of the original transmitter input signal. In FM receivers, the varying frequency is changed to a varying amplitude signal at this point. Finally, amplification occurs for the output device. Figure 1185. Over the years, with the development of transistors, microtransistors, and integrated circuits, radio transmitters and receivers have become smaller. Electronic bays were established on older aircraft as remote locations to mount radio devices simply because they would not fit in the flight deck. Today, many avionics devices are small enough to be mounted in the instrument panel, which is customary on most light aircraft. Because of the number of communication and navigation aids, as well as the need to present an uncluttered interface to the pilot, most complicated aircraft retain an area away from the flight deck for the mounting of avionics. The control heads of these units remain on the flight deck. Transceivers. A transceiver is a communication radio that transmits and receives. The same frequency is used for both. When transmitting, the receiver does not function. The push-to-talk (PTT) switch blocks the receiving circuitry and allows the transmitter circuitry to be active. In a transceiver, some of the circuitry is shared by the transmitting and receiving functions of the device. So is the antenna. This saves space and the number of components used. Transceivers are half-duplex systems where communication can occur in both directions, but only one party can speak, while the other must listen. VHF aircraft communication radios are usually transceivers. Figure 1186. Antennas. As stated, antennas are conductors that are used to transmit and receive radio frequency waves. Although the airframe technician has limited duties in relation to maintaining and repairing avionics, it is the responsibility of the technician to install, inspect, repair, and maintain aircraft radio antennas. Length. When an AC signal is applied to an antenna, it has a certain frequency. There is a corresponding wavelength for that frequency. An antenna that is half the length of this wavelength is resonant. During each phase of the applied AC, all voltage and current values experience the full range of their variability. As a result, an antenna that is half the wavelength of the corresponding AC frequency is able to allow full voltage and full current flow for the positive phase of the AC signal in one direction. The negative phase of the full AC sine wave is accommodated by the voltage and current simply changing direction in the conductor. Thus, the applied AC frequency flows through its entire wavelength, first in one direction and then in the other. This produces the strongest signal to be radiated by the transmitting antenna. It also facilitates capture of the wave and maximum induced voltage in the receiving antenna. Figure 1187. Most radios, especially communication radios, use the same antenna for transmitting and receiving. Multi-channel radios could use a different length antenna for each frequency. However, this is impractical. Acceptable performance can exist from a single antenna, half the wavelength of a median frequency. This antenna can be made effectively shorter by placing a properly rated capacitor in series with the transmission line from the transmitter or receiver. This electrically shortens the resonant circuit of which the antenna is a part. An antenna may be electrically lengthened by adding an inductor in the circuit. Adjusting antenna length in this fashion allows the use of a single antenna for multiple frequencies in a narrow frequency range. Many radios use a tuning circuit to adjust the effective length of the antenna to match the wavelength of the desired frequency. It contains a variable capacitor and an inductor connected in parallel in a circuit. Newer radios use a more efficient tuning circuit. It uses switches to combine frequencies from crystal-controlled circuits to create a resonant frequency that matches the desired frequency. Either way, the physical antenna length is a compromise when using a multi-channel communication or navigation device that must be electronically tuned for the best performance. A formula can be used to find the ideal length of a half-wavelength antenna required for a particular frequency as follows. Antenna length, feet, equals 468 f megahertz. The formula is derived from the speed of propagation of radio waves, which is approximately 300 million meters per second. It takes into account the dielectric effect of the air at the end of an antenna that effectively shortens the length of the conductor required. VHF radio frequencies used by aircraft communication radios are 118 to 136.975 MHz. The corresponding half wavelengths of these frequencies are 3.96 to 3.44 feet, 47.5 to 41.2 inches. Therefore, VHF antennas are relatively long. Antennas 1/4 of the wavelength of the transmitted frequency are often used. This is possible because when mounted on a metal fuselage, a ground plane is formed and the fuselage acts as the missing 1/4 length of the half wavelength antenna. This is further discussed in the following antenna types section: polarization, directivity, and field pattern. Antennas are polarized. They radiate and receive in certain patterns and directions. The electric field caused by the voltage in the conductor is parallel to the polarization of an antenna. It is caused by the voltage difference between each end of the antenna. The electromagnetic field component of the radio wave is at 90 degrees to the polarization. It is caused by changing current flow in the antenna. These fields were illustrated in Figure 1176 and 1177. As radio waves radiate out from the antenna, they propagate in a specific direction and in a specific pattern. This is the antenna field. The orientation of the electric and electromagnetic fields remains at 90 degrees to each other, but radiate from antenna with varying strength in different directions. The strength of the radiated field varies depending on the type of antenna and the angular proximity to it. All antennas, even those that are omnidirectional, radiate a stronger signal in some direction compared to other directions. This is known as the antenna field directivity. Receiving antennas with the same polarization as the transmitting antenna generate the strongest signal. A vertically polarized antenna is mounted up and down. It radiates waves out from it in all directions. To receive the strongest signal from these waves, the receiving antenna should also be positioned vertically so the electromagnetic component of the radio wave can cross it at as close to a 90-degree angle as possible for most of the possible proximities. Figure 1188. Horizontally polarized antennas are mounted side to side, horizontally. They radiate in a donut-like field. The strongest signals come from, or are received at, 90 degrees to the length of the antenna. There is no field generated off of the end of the antenna. Figure 1189 illustrates the field produced by a horizontally polarized antenna. Many vertical and horizontal antennas on aircraft are mounted at a slight angle off plane. This allows the antenna to receive a weak signal rather than no signal at all when the polarization of the receiving antenna is not identical to the transmitting antenna. Figure 1190. Types. There are three basic types of antennas used in aviation: dipole antenna, Marconi antenna, loop antenna, dipole antenna. The dipole antenna is the type of antenna referred to in the discussion of how a radio wave is produced. It is a conductor, the length of which is approximately equal to half the wavelength of the transmission frequency. This sometimes is referred to as a Hertz antenna. The AC transmission current is fed to a dipole antenna in the center. As the current alternates, current flow is greatest in the middle of the antenna and gradually less as it approaches the ends. Then it changes direction and flows the other way. The result is that the largest electromagnetic field is in the middle of the antenna, and the strongest radio wave field is perpendicular to the length of the antenna. Most dipole antennas in aviation are horizontally polarized. A common dipole antenna is the V-shaped VHF navigation antenna, known as a VOR antenna, found on numerous aircraft. Each arm of the V is 1/4 wavelength, creating a half-wave antenna which is fed in the center. This antenna is horizontally polarized. For a dipole receiving antenna, this means it is most sensitive to signals approaching the antenna from the sides rather than head-on in the direction of flight. Figure 1191. Marconi antenna. A Marconi antenna is a 1/4 wave antenna. It achieves the efficiency of a half-wave antenna by using the mounting surface of the conductive aircraft skin to create the second 1/4 wavelength. Most aircraft VHF communications antennas are Marconi antennas. They are vertically polarized and create a field that is omnidirectional. On fabric-skinned aircraft, the ground plane that makes up the second 1/4 wavelength of the antenna must be fashioned under the skin, where the Marconi antenna is mounted. This can be done with thin aluminum or aluminum foil. Sometimes 4 or more wires are extended under the skin from the base of the vertical antenna that serve as the ground plane. This is enough to give the antenna the proper conductive length. The same practice is also utilized on ground-based antennas. Figure 1192. Loop antenna. The third type of antenna commonly found on aircraft is the loop antenna. When the length of an antenna conductor is fashioned into a loop, its field characteristics are altered significantly from that of a straight half wavelength antenna. It also makes the antenna more compact and less prone to damage. Used as a receiving antenna, the loop antenna's properties are highly direction sensitive. A radio wave intercepting the loop directly broadside causes equal current flow in both sides of the loop. However, the polarity of the current flows is opposite each other. This causes them to cancel out and produce no signal. When a radio wave strikes the loop antenna in line with the plane of the loop, current is generated first in one side and then in the other side. This causes the current flows to have different phases, and the strongest signal can be generated from this angle. The phase difference and strength of the generated current varies proportionally to the angle at which the radio wave strikes the antenna loop. This is useful and is discussed further in the section on Automatic Direction Finder, ADF, Navigational Aids. Figure 1193. Transmission lines. Transmitters and receivers must be connected to their antennas via conductive wire. These transmission lines are coaxial cable, also known as coax. Coax consists of a center wire conductor surrounded by a semi-rigid insulator. Surrounding the wire and insulator material is a conductive braided cover that runs the length of the cable. Finally, a waterproof covering is set around the braided shield to protect the entire assembly from the elements. The braided cover in the coax shields the inner conductor from any external fields. It also prevents the fields generated by the internal conductor from radiating. For optimum performance, the impedance of the transmission line should be equal to the impedance of the antenna. In aviation antenna applications, this is often approximately 50 ohms. Figure 1194. Special connectors are used for coaxial cable. A variety can be seen in Advisory Circular, AC, 43.131b, Chapter 11, Section 17, Figure 1137. The technician should follow all manufacturers' instructions when installing transmission lines and antenna. Correct installation is critical to radio and antenna performance. Radio navigation. In the early years of aviation, a compass, a map, and dead reckoning were the only navigational tools. These were marginally reassuring if weather prevented the pilot from seeing the terrain below. Voice radio transmission from someone on the ground to the pilot, indicating that the aircraft could be heard overhead, was a preview of what electronic navigational aids could provide. For aviation to reach fruition as a safe, reliable, consistent means of transportation, some sort of navigation system needed to be developed. Early flight instruments contributed greatly to flying when the ground was obscured by clouds. Navigation aids were needed to indicate where an aircraft was over the Earth as it progressed toward its destination. In the 1930s and 1940s, a radio navigation system was used that was a low-frequency, 4-course radio range system. Airports and selected navigation waypoints broadcast 2 Morse code signals with finite ranges and patterns. Pilots tuned to the frequency of the broadcasts and flew in an orientation pattern until both signals were received with increasing strength. The signals were received as a blended tone of the highest volume when the aircraft was directly over the broadcast area. From this beginning, numerous refinements to radio navigational aids developed. Radio navigation aids supply the pilot with intelligence that maintains or enhances the safety of flight. As with communication radios, navigational aids are avionics devices, the repair of which must be carried out by trained technicians at certified repair stations. However, installation, maintenance and proper functioning of the electronic units, as well as their antennas, displays, and any other peripheral devices are the responsibilities of the airframe technician. VOR navigation system. One of the oldest and most useful navigational aids is the Very High Frequency Omnidirectional Range, VOR, navigation system. The 4 main components of a typical system are a receiver, a visual indicator, a frequency selector, controller or control panel, and antennas. The system was constructed after World War II and is still in use today. It consists of thousands of land-based transmitter stations, or VORs, that communicate with radio receiving equipment on board aircraft. Many of the VORs are located along airways. The Victor airway system is built around the VOR navigation system. Ground VOR transmitter units are also located at airports where they are known as TVOR, Terminal VOR. The U.S. military has a navigational system known as TACAN that operates similarly to the VOR system. Sometimes VOR and TACAN transmitters share a location. These sites are known as VORTACs. The position of all VORs, TVORs and VORTACs are marked on aeronautical charts, along with the name of the station, the frequency to which an airborne receiver must be tuned to use the station, and a Morse code designation for the station. Some VORs also broadcast a voice identifier on a separate frequency that is included on the chart, figure 1195. VOR uses VHF radio waves, 108 to 117.95 MHz, with 50 kHz separation between each channel. This keeps atmospheric interference to a minimum, but limits the VOR to line-of. Site usage. To receive VOR VHF radio waves, generally a V-shaped, horizontally polarized bipole antenna is used. Other type antennas are also certified. Follow the manufacturer's instructions for installation location, figure 1196. The signals produced by a VOR transmitter propagate 360 degrees from the unit and are used by aircraft to navigate to and from the station with the help of an onboard VOR receiver and display instruments. A pilot is not required to fly a pattern to intersect the signal from a VOR station, since it propagates out in every direction. The radio waves are received as long as the aircraft is in range of the ground unit and regardless of the aircraft's direction of travel. Figure 1197. A VOR transmitter produces 2 signals that a receiver on board an aircraft uses to locate itself in relation to the ground station. One signal is a reference signal. The second is produced by electronically rotating a variable signal. The variable signal is in phase with the reference signal when at magnetic north, but becomes increasingly out of phase as it is rotated to 180 degrees. As it continues to rotate to 360 degrees 0 degrees, the signals become increasingly in phase until they are in phase again at magnetic north. The receiver in the aircraft deciphers the phase difference and determines the aircraft's position in degrees from the VOR ground-based unit, figure 1198. Most aircraft carry a dual VOR receiver. Sometimes the VOR receivers are part of the same avionics unit as the VHF communication transceivers. These are known as NAV/COM radios. Internal components are shared since frequency bands for each are adjacent, figure 1199. Large aircraft may have two dual receivers and even dual antennas. Normally, one receiver is selected for use, and the second is tuned to the frequency of the next VOR station to be encountered en route. A means for switching between NAV1 and NAV2 is provided, as is a switch for selecting the active or standby frequency. Figure 11100. VOR receivers are also found coupled with Instrument Landing System ILS receivers and glide slope receivers. AVOR receiver interprets the bearing in degrees to or from the VOR station where the signals are generated. It also produces DC voltage to drive the display of the deviation from the desired course centerline to or from the selected station. Additionally, the receiver decides whether or not the aircraft is flying toward the VOR or away from it. These items can be displayed a number of different ways on various instruments. Older aircraft are often equipped with a VOR gauge dedicated to display only VOR information. This is also called an omni-bearing selector, OBS, or a course. Deviation indicator, CDI. Figure 11101. The CDI linear indicator remains essentially vertical, but moves left and right across the graduations on the instrument face to show deviation from being on course. Each graduation represents 2 degrees. The OBS knob rotates the azimuth ring. When in range of a VOR, the pilot rotates the OBS until the course deviation indicator centers. For each location of an aircraft, the OBS can be rotated to 2 positions where the CDI will center. One produces an arrow in the TO window of the gauge, indicating that the aircraft is traveling toward the VOR station. The other selectable bearing is 180 degrees from this. When chosen, the arrow is displayed in the from window, indicating the aircraft is moving away from the VOR on the course selected. The pilot must steer the aircraft to the heading with the CDI centered to fly directly to or from the VOR. The displayed VOR information is derived from deciphering the phase relationship between the 2 simultaneously transmitted signals from the VOR ground station. When power is lost or the VOR signal is weak or interrupted, a NAV warning flag comes into view, figure 11101. A separate gauge for the VOR information is not always used. As flight instruments and displays have evolved, VOR navigation information has been integrated into other instruments' displays, such as the radio magnetic indicator, RMI, the HSI, an EFIS display, or an electronic attitude director indicator, EADI. Flight management systems and automatic flight control systems are also made to integrate VOR information to automatically control the aircraft on its planned flight segments. Flat panel MFDs integrate VOR information into moving map presentations and other selected displays. The basic information of the radial bearing in degrees, course deviation indication, and to from information remains unchanged, however. Figure 11102. At large airports, an Instrument Landing System, ILS, guides the aircraft to the runway while on an instrument landing approach. The aircraft's VOR receiver is used to interpret the radio signals. It produces a more sensitive course deviation indication on the same instrument display as the VORCDI display. This part of the ILS is known as the localizer and is discussed below. While tuned to the ILS localizer frequency, the VOR circuitry of the VOR ILS receiver is inactive. It is common at VOR stations to combine the VOR transmitter with distance measuring equipment, DME, or a non-directional beacon, NDB, such as an ADF transmitter and antenna. When used with a DME, pilots can gain an exact fix on their location using the VOR and DME together. Since the VOR indicates the aircraft's bearing to the VOR transmitter and a co-located DME indicates how far away the station is, this relieves the pilot from having to fly over the station to the area concerned. Specific points on the airport surface are given to perform the test. Most VOTs require tuning 108.0 MHz on the VOR receiver and centering the CDI. The OBS should indicate 0 degrees showing from on the indicator or 180 degrees when showing TU. If an RMI is used as the indicator, the test heading should always indicate 180 degrees. Some repair stations can also generate signals to test VOR receivers, although not on 108.0 MHz. Contact the repair station for the transmission frequency and for their assistance in checking the VOR system. A logbook entry is required. Note: some airborne testing using VOTs is possible by the pilot. An error of plus or minus 4 degrees should not be exceeded when testing a VOR system with a VOT. An error in excess of this prevents the use of the aircraft for instrument flight rules flight until repairs are made. Aircraft having dual VOR systems, where only the antenna is shared, may be tested by comparing the output of each system to the other. Tune the VOR receivers to the local ground VOR station. A bearing indication difference of no more than plus or minus 4 degrees is permissible. Know with certainty their location. These navigational aids are discussed separately in the following sections. Automatic Direction Finder, ADF. An automatic direction finder, ADF, operates off of A. Functional accuracy of VOR equipment is critical to the safety ground signal transmitted from a NDB, early radio direction of flight. VOR receivers are operationally tested using VOR finders. RDF used the same principle, a vertically polarized test facilities VOT. These are located at numerous airports. Antenna was used to transmit LF frequency radio waves in. Radiomagnetic indicator, RMI. To save space in the instrument panel and to consolidate related information into one easy-to-use location, the radiomagnetic indicator, RMI, has been developed. It is widely used. The RMI combines indications from a magnetic compass, VOR, and ADF into one instrument. Figure 11,109. The azimuth card of the RMI is rotated by a remotely located flux gate compass. Thus, the magnetic heading of the aircraft is always indicated. The lubber line is usually a marker or triangle at the top of the instrument dial. The VOR receiver drives the solid pointer to indicate the magnetic direction to a tuned VOR station. When the ADF is tuned to an NDB, the double or hollow pointer indicates the magnetic bearing to the NDB. Since the flux gate compass continuously adjusts the azimuth card so that the aircraft heading is at the top of the instrument, pilot workload is reduced. The pointers indicate where the VOR and ADF transmission stations are located in relationship to where the aircraft is currently positioned. Push buttons allow conversion of either pointer to either ADF or VOR for navigation involving two of one type of station and none of the other. Instrument Landing Systems, ILS. An ILS is used to land an aircraft when visibility is poor. This radio navigation system guides the aircraft down a slope to the touchdown area on the runway. Multiple radio transmissions are used that enable an exact approach to landing with an ILS. A localizer is one of the radio transmissions. It is used to provide horizontal guidance to the center line of the runway. A separate glide slope broadcast provides vertical guidance of the aircraft down the proper slope to the touchdown point. Compass locator transmissions for outer and middle approach. Marker beacons aid the pilot in intercepting the localizer. The localizer broadcast is a VHF broadcast in the lower range of the VOR frequencies, 108 MHz to 111.95 MHz, on odd frequencies only. Two modulated signals are produced from a horizontally polarized antenna complex beyond the far end of the approach runway. They create an expanding field that is 2.5 degrees wide, about 1,500 feet, 5 miles from the runway. The field tapers to runway width near the landing threshold. The left side of the approach area is filled with a VHF carrier wave modulated with a 90 Hz signal. The right side of the approach contains a 150 MHz modulated signal. The aircraft's VOR receiver is tuned to the localizer VHF frequency that can be found on published approach plates and aeronautical charts. The circuitry specific to standard VOR reception is inactive, while the receiver uses localizer circuitry and components common to both. The signals received are passed through filters and rectified into DC to drive the course deviation indicator. If the aircraft receives a 150 Hz signal, the CDI of the VOR ILS display deflects to the left. This indicates that the runway is to the left. The pilot must correct course with a turn to the left. This centers the course deviation indicator on the display and centers the aircraft with the centerline of the runway. If the 90 Hz signal is received by the VOR receiver, the CDI deflects to the right. The pilot must turn toward the right to center the CDI and the aircraft with the runway center line. Figure 11,111. Glide slope. The vertical guidance required for an aircraft to descend for a landing is provided by the glide slope of the ILS. The glide slope provides vertical guidance for correct angle of descent. Radio signals funnel the aircraft down to the touchdown point on the runway at an angle of approximately 3 degrees. The transmitting glide slope antenna is located off to the side of the approach runway, approximately 1,000 feet from the threshold. It transmits in a wedge-like pattern, with the field narrowing as it approaches the runway. Figure 11,112. The glide slope transmitter antenna is horizontally polarized. The transmitting frequency range is UHF between 329.3 MHz and 335.0 MHz. The frequency is paired to the localizer frequency of the ILS. When the VOR ILS receiver is tuned for the approach, the glide slope receiver is automatically tuned. Like the localizer, the glide slope transmits two signals, one modulated at 90 Hz and the other modulated at 150 Hz. The aircraft's glide slope receiver deciphers the signals similar to the method of the localizer receiver. It drives a vertical course deviation indicator known as the glide slope indicator. The glide slope indicator operates identically to the localizer CDI, only 90 degrees to it. The VOR ILS localizer CDI and the glide slope are displayed together on whichever kind of instrumentation is in the aircraft. Figure 11,113. The UHF antenna for aircraft reception of the glide slope signals comes in many forms. A single dipole antenna mounted inside the nose of the aircraft is a common option. Antenna manufacturers have also incorporated glide slope reception into the same dipole antenna used for the VHS VORILS localizer reception. Blade-type antennas are also used. Figures 11,114. Figure 11,115 shows a VOR and a glide slope receiver for a GA aircraft ILS. Compass locators. It is imperative that a pilot be able to intercept the ILS to enable its use. A compass locator is a transmitter designed for this purpose. There is typically one located at the outer marker beacon 4 to 7 miles from the runway threshold. Another may be located at the middle marker beacon about 3,500 feet from the threshold. The outer marker compass locator is a 25-watt NDB with a range of about 15 miles. It transmits omnidirectional LF radio waves, 190 Hz to 535 Hz, keyed with the first 2 letters of the ILS identifier. The ADF receiver is used to intercept the locator, so no additional equipment is required. If a middle marker compass locator is in place, it is similar but is identified with the last 2 letters of the ILS identifier. Once located, the pilot maneuvers the aircraft to fly down the glide path to the runway. Marker beacons. Marker beacons are the final radio transmitters used in the ILS. They transmit signals that indicate the position of the aircraft along the glide path to the runway. As mentioned, an outer marker beacon transmitter is located 4 to 7 miles from the threshold. It transmits a 75 MHz carrier wave modulated with a 400 Hz audio tone in a series of dashes. The transmission is very narrow and directed straight up. A marker beacon receiver receives the signal and uses it to light a blue light on the instrument panel. This, plus the aural tone in combination with the localizer and the glide slope indicator, positively locates the aircraft on an approach. Figure 11,115. A middle marker beacon is also used. It is located on approach approximately 3,500 feet from the runway. It also transmits at 75 MHz. The middle marker transmission is modulated with a 1300 Hz tone that is a series of dots and dashes, so as to not be confused with the all-dash tone of the outer marker. When the signal is received, it is used in the receiver to illuminate an amber-colored light on the instrument panel. Figure 11,116. Some ILS approaches have an inner marker beacon that display aircraft usually incorporate marker lights or indicators. Distance measuring equipment, DME. Many VOR stations are co-located with the military version of the VOR station, which is known as TACAN. When this occurs, the navigation station is known as a VORTAC station. Civilian aircraft make use of one of the TACAN features not originally installed at civilian VOR stations, DME. A DME system calculates the distance from the aircraft to the DME unit at the VORTAC ground station and displays it on the flight deck. It can also display calculated aircraft speed and elapsed time for arrival when the aircraft is traveling to the station. DME ground stations have subsequently been installed at civilian VORs as well as in conjunction with ILS localizers. These are known as VOR-DME and ILS-DME or LOC-DME. The latter aid in approach to the runway during landings. The DME system consists of an airborne DME transceiver, display and antenna, as well as the ground-based DME unit and its antenna. Figure 11,119. The DME is useful because with the bearing from the VOR and the distance to a known point, the DME antenna at the VOR, a pilot can positively identify the location of the aircraft. DME operates in the UHF frequency range from 962 MHz to 1,213 MHz. a carrier signal transmitted from Figure 11-115, a localizer and glide slope receiver for a general aviation aircraft ILS. And returned is calculated and converted into nautical miles for display. Time to station and speed are also calculated and displayed. DME readout can be on a dedicated DME display, or it can be part of an EHSI, EADI, EFIS, or on the primary flight display in a glass flight deck. Figure 11-120. The DME frequency is paired to the co-located VOR or VOR-TAC frequency. When the correct frequency is tuned for the VOR signal, the DME is tuned automatically. Tones are broadcast for the VOR station identification and then for the DME. The hold selector on a DME panel keeps the DME tuned in while the VOR selector is tuned to a different VOR. In most cases, the UHF of the DME is transmitted and received via a small blade-type antenna mounted to the underside of the fuselage centerline. Figure 11-121. A traditional DME displays the distance from the DME transmitter antenna to the aircraft. This is called the slant distance. It is very accurate. However, since the aircraft is at altitude, the distance to the DME ground antenna from a point directly beneath the aircraft is shorter. Some modern DMEs are equipped to calculate this ground distance and display it. Figure 11,122. Area Navigation, RNAV. Area Navigation, RNAV, is a general term used to describe the navigation from point A to point B without direct overflight of navigational aids, such as VOR stations or ADF, non-directional beacons. It includes VORTAC and VOR DME-based systems, as well as systems of RNAV based around LoRaWAN, GPS, INS, and the FMS of transport. All RNAV systems make use of waypoints. A waypoint is a designated geographical location or point used for route definition or progress reporting purposes. It can be defined or described by using latitude-longitude grid coordinates or, in the case of VOR-based RNAV, described as a point on a VOR radial, followed by that point's distance from the VOR station, i.e., 225 means a point 25 nautical miles from the VOR station on the 200-degree radial. All RNAV systems make use of waypoints. A waypoint is a designated geographical location or point used for route definition or progress reporting purposes. It can be defined or described by using latitude-longitude grid coordinates or, in the case of VOR-based RNAV, described as a point on a VOR radial, followed by that point's distance from the VOR station, i.e., 225 means a point 25 nautical miles from the VOR station on the 200-degree radial. Figure 11,123 illustrates an RNAV route of flight from Airport A to Airport B. The VOR, DME, and VORTAC stations shown are used to create phantom waypoints that are overflown rather than the actual stations. This allows a more direct route to be taken. The phantom waypoints are entered into the RNAV courseline computer CLC as a radial and distance number pair. The computer creates the waypoints and causes the aircraft's CDI to operate as though they are actual VOR stations. A mode switch allows the choice between standard VOR navigation and RNAV. VOR-based RNAV uses the VOR receiver, antenna, and VOR display equipment, such as the CDI. The computer in the RNAV unit uses basic geometry and trigonometry calculations to produce heading, speed, and time readouts for each waypoint. VOR stations need to be within line of sight and operational range from the aircraft for RNAV use. Figure 11,124. RNAV has increased in flexibility with the development of GPS. Integration of GPS data into a planned VOR-RNAV flight plan is possible, as is GPS route planning without the use of any VOR stations. Radar beacon transponder. A radar beacon transponder, or simply a transponder, provides positive identification and location of an aircraft on the radar screens of ATC. For each aircraft equipped with an altitude encoder, the transponder also provides the pressure altitude of the aircraft to be displayed adjacent to the on-screen blip that represents the aircraft. Figure 11,125. Radar capabilities at airports vary. Generally, two types of radar are used by Air Traffic Control, ATC. The primary radar transmits directional UHF or SHF radio waves sequentially in all directions. When the radio waves encounter an aircraft, part of those waves reflect back to a ground antenna. Calculations are made in a receiver to determine the direction and distance of the aircraft from the transmitter. A blip or target representing the aircraft is displayed on a radar screen, also known as a Plan Position Indicator, PPI. The azimuth direction and scaled distance from the tower are presented, giving controllers a two-dimensional fix on the aircraft. Figure 11,126. A secondary surveillance radar, SSR, is used by ATC to verify the aircraft's position and to add the third dimension of altitude to its location. SSD radar transmits coded pulse trains that are received by the transponder on board the aircraft. Mode 3A pulses, as they are known, aid in confirming the location of the aircraft. When verbal communication is established with ATC, a pilot is instructed to select one of 4,096 discrete codes on the transponder. These are digital octal codes. The ground station transmits a pulse of energy at 130 MHz, and the transponder transmits a reply with transponder tests and inspections. Title 14 of the Code of Federal Regulations, CFR, Part 91, Section 91.413 states that all transponders on aircraft flown into controlled airspace are required to be inspected and tested in accordance with 14 CFR Part 43, Appendix F, every 24 calendar months. Installation or maintenance that may introduce a transponder error is also cause for inspection and test in accordance with Appendix F. Only an appropriately rated repair station, the aircraft manufacturer, if it installed transponder, and holders of a continuous airworthy program are approved to conduct the procedures. As with many radioelectronic devices, test equipment exists to test airworthy operation of a transponder. Figure 11,129. Operating a transponder in a hangar or on the ramp does not immunize it from interrogation and reply. Transmission of certain codes reserved for emergencies or military activity must be avoided. The procedure to select a code during ground operation is to do so with the transponder in the off or standby mode to avoid inadvertent transmission. Code 0000 is reserved for military use and is a transmittable code. Code 7500 is used in a hijack situation, and 7600 and 7700 are also reserved for emergency use. Even the inadvertent transmission of code 1200, reserved for VFR flight not under ATC direction, could result in evasion action. All signals received from a radar beacon transponder are taken seriously by ATC. Altitude encoders. Altitude encoders convert the aircraft's pressure altitude into a code sent by the transponder to ATC. Increments of 100 feet are usually reported. Encoders have varied over the years. Some are built into the altimeter instrument used in the instrument panel and connected by wires to the transponder. Others are mounted out of sight on an avionics rack or similar out-of-the-way place. These are known as blind encoders. On transport category aircraft, the altitude encoder may be a large black box with a static line connection to an internal aneroid. Modern general aviation encoders are smaller and more lightweight, but still often feature an internal aneroid and static line connection. Some encoders use microtransistors and are completely solid state, including the pressure sensing device from which the altitude is derived. No static port connection is required. Data exchange with GPS and other systems is becoming common. Figure 11,130. When a transponder selector is set on ALT, the digital pulse message sent in response to the secondary surveillance radar interrogation becomes the digital representation of the pressure altitude of the aircraft. There are 1,280 altitude codes, one for each 100 feet of altitude between 1,200 feet, mean sea level, MSL, and 126,700 feet, MSL. Each altitude increment is assigned a code. While these would be 1,280 of the same codes used for location and ident, the Mode C or S interrogation deactivates the 4,096 location codes and causes the encoder to become active. The correct altitude code is sent to the transponder that replies to the interrogation. The SSR receiver recognized this as a response to a Mode C or S interrogation and interprets the code as altitude code. Collision avoidance systems. The ever-increasing volume of air traffic has caused a corresponding increase in concern over collision avoidance. Ground-based radar, traffic control, and visual vigilance are no longer adequate in today's increasingly crowded skies. Onboard collision avoidance equipment, long a staple in larger aircraft, is now common in general aviation aircraft. New applications of electronic technology combined with lower costs make this possible. Traffic Collision Avoidance Systems, TCAS. Traffic Collision Avoidance Systems, TCAS, are transponder-based air-to-air traffic monitoring and alerting systems. There are two classes of TCAS. TCAS was developed to accommodate the general aviation community and regional airlines. This system identifies traffic in a 35 to 40-mile range of the aircraft and issues traffic advisories to assist pilots in visual acquisition of intruder aircraft. TCAS is mandated on aircraft with 10 to 30 seats. TCAS-2 is a more sophisticated system. It is required internationally in aircraft with more than 30 seats or weighing more than 15,000 kilograms. TCAS-2 provides the information of TCAS-1, but also analyzes the projected flight path of approaching aircraft. If a collision or near miss is imminent, the TCAS-2 computer issues a Resolution Advisory RA. This is an oral command to the pilot to take a specific evasive action, i.e. descend. The computer is programmed such that the pilot in the encroaching aircraft receives an RA for evasive action in the opposite direction, if it is TCAS-2 equipped. Figure 11,131. The transponder of an aircraft with TCAS is able to interrogate the transponders of other aircraft nearby using SSR technology, Mode C and Mode S. This is done with a 1030 MHz signal. Interrogated aircraft transponders reply with an encoded 1090 MHz signal that allows the TCAS computer to display the position and altitude of each aircraft. Should the aircraft come within the horizontal or vertical distances shown in figure 11,131, an audible TA is announced. The pilot must decide whether to take action and what action to take. TCAS-2 equipped aircraft use continuous reply information to analyze the speed and trajectory of target aircraft in close proximity. If a collision is calculated to be imminent, an RA is issued. TCAS target aircraft are displayed on a screen on the flight deck. Different colors and shapes are used to depict approaching aircraft depending on the imminent threat level. Since RAs are currently limited to vertical evasive maneuvers, some standalone TCAS displays are electronic vertical speed indicators. Most aircraft use some version of an electronic HSI on a navigational screen or page to display TCAS information. Figure 11132. A multifunction display may depict TCAS and weather radar information on the same screen. Figure 11133. A TCAS control panel, figure 11134, and computer are required to work with a compatible transponder and its antennas. Interface with EFIS or other previously installed or selected display is also required. TCAS may be referred to as Airborne Collision Avoidance System, ACAS, which is the international name for the same system. TCAS-2 with the latest revisions is known as version 7. The accuracy and reliability of this TCAS information is such that pilots are required to follow a TCAS RA over an ATC command. ADS-B. Collision avoidance is a significant part of the FAA's next-gen plan for transforming the national airspace system, NAS. Increasing the number of aircraft using the same quantity of airspace and ground facilities requires the implementation of new technologies to maintain a high level of performance and safety. The successful proliferation of global navigation satellite systems, GNSS, such as GPS, has led to the development of a collision avoidance system known as Automatic Dependent Surveillance Broadcast, ADS-B. ADS-B is an integral part of Next-Gen program. The implementation of its ground and airborne infrastructure is currently underway. ADS-B is active in parts of the United States and around the world. Figure 11135. ADS-B is considered in two segments, ADS-B out and ADS-B in. ADS-B out combines the positioning information available from a GPS receiver with onboard flight status information, i.e. location, including altitude, velocity, and time. It then broadcasts this information to other ADS-B-equipped aircraft and ground stations. Figure 11136. Two different frequencies are used to carry these broadcasts with data link capability. The first is an expanded use of the 1090 MHz Mode S transponder protocol known as 1090 ES. The second, largely being introduced as a new broadband solution for general aviation implementation of ADS-B, is at 978 MHz. A 978 Universal Access Transceiver, UAT, is used to accomplish this. An omnidirectional antenna is required in addition to the GPS antenna and receiver. Airborne receivers of an ADS-B use the information to plot the location and movement of the transmitting aircraft on a flight deck display, similar to TCAS, figure 11137. Inexpensive ground stations, compared to radar, are constructed in remote and obstructed areas to proliferate ADS-B. Ground stations share information from airborne ADS-BS with other ground stations that are part of the Air Traffic Management System, ATMS. Data is transferred with no need for human acknowledgement. Microwave and satellite transmissions are used to link the network. For traffic separation and control, ADS-B has several advantages over conventional ground-based radar. The first is the entire airspace can be covered with a much lower expense. The aging ATC radar system that is in place is expensive to maintain and replace. Additionally, ADS-B provides more accurate information since the vector state is generated from the aircraft with the help of GPS satellites. Weather is a greatly reduced factor with ADS-B. Ultra-high-frequency GPS transmissions are not affected. Increased positioning accuracy allows for higher density traffic flow and landing approaches, an obvious requirement to operate more aircraft in and out of the same number of facilities. The higher degree of control available also enables routing for fewer weather delays and optimal fuel burn rates. Collision avoidance is expanded to include runway incursion from other aircraft and support vehicles on the surface of an airport. ADS-B offers features not available in TCAS. Equipped aircraft are able to receive abundant data to enhance situational awareness. Traffic information services broadcast TISB supply traffic information from non-ADS-B aircraft and ADS-B aircraft on a different frequency. Ground radar.
GS 3S 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 3S
195 degrees, 17 hundredths, heading 297 magnetic azimuth. Plus 30, traffic. Plus 13. Plus 2 minus 2. Monitoring of surface targets and any traffic data in the linked network of ground stations is sent via ADS-B in to the flight deck. This provides a more complete picture than air-to-air only collision avoidance. Flight Information Services broadcast FISB is also received by ADS-B in. Weather text and graphics, ATIS information, and NOTAMs are able to be received in aircraft that have 987 UAT capability. Figure 11138. A radio altimeter or radar altimeter is used to measure the distance from the aircraft to the terrain directly beneath it. It is used primarily during instrument approach and low-level or night flight below 2,500 feet. The radio altimeter supplies the primary altitude information for landing decision height. It incorporates an adjustable altitude bug that creates a visual or oral warning to the pilot when the aircraft reaches that. ADS-B test units are available for trained maintenance personnel to verify proper operation of ADS-B equipment. This is critical since close tolerance of air traffic separation depends on accurate data from each aircraft and throughout all components of the ADS-B system. Figure 11139. Radio altimeter. A radio altimeter or radar altimeter is used to measure the distance from the aircraft to the terrain directly beneath it. It is used primarily during instrument approach and low-level or night flight below 2,500 feet. The radio altimeter supplies the primary altitude information for landing decision height. It incorporates an adjustable altitude bug that creates a visual or oral warning to the pilot when the aircraft reaches that altitude. Typically, the pilot will abort a landing if the decision height is reached and the runway is not visible. Using a transceiver and a directional antenna, a radio altimeter broadcasts a carrier wave at 4.3 GHz from the aircraft directly toward the ground. The wave is frequency, modulated at 50 MHz, and travels at a known speed. It strikes surface features and bounces back toward the aircraft, where a second antenna receives the return signal. The transceiver processes the signal by measuring the elapsed time the signal traveled and the frequency modulation that occurred. The display indicates height above the terrain, also known as above ground level, AGL. Figure 11140. A radar altimeter is more accurate and responsive than an air pressure altimeter for above ground level information at low altitudes. The transceiver is usually located remotely from the indicator. Multifunctional and glass flight deck displays typically integrate decision height awareness from the radar altimeter as a digital number displayed on the screen with a bug, light or color change used to indicate when that altitude is reached. Large aircraft may incorporate radio altimeter information into a ground proximity warning system, GPWS, which orally alerts the crew of potentially dangerous proximity to the terrain below the aircraft. A decision height, DH, window displays the radar altitude on the EADI in Figure 11141, weather radar. There are three common types of weather aids used in an aircraft flight deck that are often referred to as weather radar: actual onboard radar for detecting and displaying weather activity, lightning detectors, and satellite or other source weather radar information that is uploaded to the aircraft from an outside source. Onboard weather radar systems can be found in aircraft of all sizes. They function similar to ATC primary radar, except the radio waves bounce off of precipitation instead of aircraft. Dense precipitation creates a stronger return than light precipitation. The onboard weather radar receiver is set up to depict heavy returns as red, medium returns as yellow, and light returns as green on a display in the flight deck. Clouds do not create a return. Magenta is reserved to depict intense or extreme precipitation or turbulence. Some aircraft have a dedicated weather radar screen. most modern. Testing considerations for 406 MHz emergency locator transmitters. Care should be taken to prevent accidentally triggering a SAR search and rescue response. Accidental activation of an ELT will generate an emergency signal that cannot be distinguished from that of an actual emergency and could lead to expensive and frustrating searches. Moreover, the unwarranted ELT signal could tie up the emergency frequencies such that a genuine emergency signal would not be picked up. In addition, if an ELT signal is transmitted on or near an airport, it may render some radio communications channels unusable. Regardless of where the ELT is or the duration of activation, a 406 MHz beacon broadcast will be detected by at least one geostationary local user terminal, GeoLUT, and possibly every low Earth orbit local user terminal, LEOLUT, in the COSPAS-SARSAT system. Alert messages will be routed to every Mission Control Center, MCC, in the COSPAS-SARSAT system for coordination around the world, and a response will be made unless prior coordination is made with COSPAS-SARSAT and local authorities. Direct connect testing is preferred to prevent inadvertent activation of the SAR response system. Over-air testing should always be avoided if possible. Use of an antenna boot or a direct connection from test equipment to the antenna port is preferred. Testing an ELT system in a metal hanger will not guarantee the radiated signal will not be detected by the COSPAS-SARSAT system. Technicians testing ELT devices in a hangar should treat the test as if they were testing outside. When testing an ELT, a 50-ohm dummy load or antenna boot should be used to prevent the signal from being radiated into space. The signal must be attenuated to less than 51 decibels per watt, a power flux density of 37.4 decibels per watt per square meter, or a field intensity of 11.6 decibels per volt per meter. If over-air testing must be accomplished, technicians should carefully follow COSPAS-SARSAT instructions and use the built-in test message on the ELT device. The ELT test message is different from messages transmitted during an emergency, but is still detectable by the COSPAS-SARSAT system. COSPAS-SARSAT should be contacted prior to performing over-air testing. COSPAS-SARSAT can be contacted at www.cospasarsat.inti/n/. If over-air testing must be accomplished, the local air traffic control ATC facility should be contacted in advance. Follow test set instructions or place the test set a minimum of 12 meters, 39.4 feet, from the ELT antenna. Test in each mode and frequency the ELT unit transmits. 406 MHz testing. Verify the device is outputting a signal of not less than 17 decibels milliwatt and not greater than 26 decibels milliwatt. Verify the device is transmitting on the correct frequency. This can be done by running the ELT self-test and detecting the signal with an ELT test set. Receiving and decoding a test message is an indication the unit is transmitting on a correct frequency. Using appropriate test equipment and shielding, note the ELT code transmitted and verify that the ELT code is registered with COSPAS-SARSAT. The testing technician or aircraft owner should verify the information on file with COSPAS-SARSAT is accurate and up to date. Determine that the ELT oral indicator can be heard in the flight deck with the aircraft engines off, and that the visual indicator can be seen from the crew's normal sitting position. If possible, this should be performed in a way that will prevent a SAR response, e.g., with a dummy load installed. Perform an operational check of the G-switch. This should be performed in a way that will prevent a SAR response, e.g., with a dummy load installed. Replace if the G-switch fails to activate. Ensure all cables except the 406 MHz transmitter output are reconnected. Ensure the 406 MHz transmitter is connected to a test set if possible. Activate the ELT, use the remote switch if installed, and determine if the system is radiating a strong 406 MHz signal. Ensure the system is reset if necessary. If equipped with a water-activated circuit, connect the ELT to a test set if possible. Activate the ELT by shorting the water sensing leads and determine if the system is radiating a strong 406 MHz signal. Ensure the system is reset if necessary. Long-Range Aid to Navigation System, LORAN. Long-Range Aid to Navigation System, LORAN, is a type of RNAV that is no longer available in the United States. It was developed during World War II, and the most recent edition, LORANC, has been very useful and accurate to aviators as well as maritime sailors. LORAN uses radio wave pulses from a series of towers and an onboard receiver, computer, to positively locate an aircraft amid the tower network. There are 12 LORAN transmitter tower chains constructed across North America. Each chain has a master transmitter tower and a handful of secondary towers. All broadcasts from the transmitters are at the same frequency, 100 kHz. Therefore, a LORAN receiver does not need to be tuned. Being in the low frequency range, the LORAN transmissions travel long distances and provide good coverage from a small number of stations. Precisely timed, synchronized pulse signals are transmitted from the towers in a chain. The LORAN receiver measures the time to receive the pulses from the master tower and 2 other towers in the chain. It calculates the aircraft's position based on the intersection of parabolic curves representing elapsed signal times from each of these known points. The accuracy and proliferation of GPS navigation has caused the U.S. government to cease support for the LORAN navigation system, citing redundancy and expense of operating the towers as reasons. Panel-mounted LORAN navigation units will likely be removed and replaced by GPS units in aircraft that have not already done so. Figure 11,151. Global Positioning System, GPS. Global Positioning System (GPS) navigation is the fastest growing type of navigation in aviation. It is accomplished through the use of Navstar satellites set and maintained in orbit around the Earth by the U.S. government. Continuous coded transmissions from the satellites facilitate locating the position of an aircraft equipped with a GPS receiver with extreme accuracy. GPS can be utilized on its own for en route navigation, or it can be integrated into other navigation systems, such as VOR-RNAV, inertial reference, or flight management systems. There are 3 segments of GPS: the space segment, the control segment, and the user segment. Aircraft technicians are only involved with user segment equipment, such as GPS receivers, displays, and antennas. 24 satellites, 21 active, 3 spares, in 6 separate planes of orbit, 12,625 miles above the planet, comprise what is known as the space segment of the GPS system. The satellites are positioned such that in any place on Earth at any one time, at least 4 will be a minimum of 15 degrees above the horizon. Typically, between 5 and 8 satellites are in view. Figure 11,152. 2 signals loaded with digitally coded information are transmitted from each satellite. The L1 channel transmission on a 1575.42 MHz carrier frequency is used in civilian aviation. Satellite identification, position, and time are conveyed to the aircraft GPS receiver on this digitally modulated signal, along with status and other information. An L2, channel 1227.60, megahertz transmission is used by the military. The amount of time it takes for signals to reach the aircraft GPS receiver from transmitting satellites is combined with each satellite's exact location to calculate the position of an aircraft. The control segment of the GPS monitors each satellite to ensure its location and time are precise. This control is accomplished with 5 ground-based receiving stations, a master control station, and 3 transmitting antennas. The receiving stations forward status information received from the satellites to the master control station. Calculations are made and corrective instructions are sent to the satellites via the transmitters. The user segment of the GPS is comprised of the thousands of receivers installed in aircraft, as well as every other receiver that uses the GPS transmissions. Specifically, for the aircraft technician, the user section consists of a control panel display, the GPS receiver circuitry, and an antenna. The control, display and receiver are usually located in a single unit, which also may include VOR ILS circuitry and a VHF communications transceiver. GPS intelligence is integrated into the multifunctional displays of glass flight deck aircraft. Figure 11153. The GPS receiver measures the time it takes for a signal to arrive from 3 transmitting satellites. Since radio waves travel at 186,000 miles per second, the distance to each satellite can be calculated. The intersection of these ranges provides a 2-dimensional position of the aircraft. It is expressed in latitude/longitude coordinates. By incorporating Wide Area Augmentation System, WAAS, to increase the accuracy of GPS for aircraft navigation, the Wide Area Augmentation System, WAAS, was developed. It consists of approximately 25 precisely surveyed ground stations that receive GPS signals and ultimately transmit correction information to the aircraft. An overview of WAAS components and its operation is shown in Figure 11154. WAAS ground stations receive GPS signals and forward position errors to 2 master ground stations. Time and location information is analyzed and correction instructions are sent to communication satellites in geostationary orbit over the NAS. The satellites broadcast GPS-like signals that WAAS-enabled GPS receivers use to correct position information received from GPS satellites. A WAAS-enabled GPS receiver is required to use the Wide Area Augmentation System. If equipped, an aircraft qualifies to perform precision approaches into thousands of airports without any ground-based approach equipment. Separation minimums are also able to be reduced between aircraft that are WAAS equipped. The WAAS system is known to reduce position errors to 1 to 3 meters laterally and vertically. Inertial Navigation System, INS. Inertial Reference System, IRS. An inertial navigation system, INS, is used on some large aircraft for long-range navigation. This may also be identified as an inertial reference system, IRS, although the IRS designation is generally reserved for more modern systems. An INS-IRS is a self-contained system that does not require input radio signals from a ground navigation facility or transmitter. The system derives attitude, velocity, and direction information from measurement of the aircraft's accelerations given a known starting point. The location of the aircraft is continuously updated through calculations based on the forces experienced by INS accelerometers. A minimum of 2 accelerometers is used, one reference to north and the other reference to east. In older units, they are mounted on a gyro-stabilized platform. This averts the introduction of errors that may result from acceleration due to gravity. An INS uses complex calculation made by an INS computer to convert applied forces into location information. An interface control head is used to enter starting location position data while the aircraft is stationary on the ground. This is called initializing. Figure 11,155. From then on, all motion of the aircraft is sensed by the built-in accelerometers and run through the computer. Feedback and correction loops are used to correct for accumulated error as flight time progresses. The amount an INS is off in 1 hour of flight time is a reference point for determining performance. Accumulated error of less than 1 mile after 1 hour of flight is possible. Continuous accurate adjustment to the gyro-stabilized platform to keep it parallel to the Earth's surface is a key requirement to reduce accumulated error. A latitude/longitude coordinate system is used when giving the location output. INS is integrated into an airliner's flight management system and automatic flight control system. Waypoints can be entered for a predetermined flight path, and the INS will guide the aircraft to each waypoint in succession. Integration with other Navi aids is also possible to ensure continuous correction and improved accuracy, but is not required. Modern INS systems are known as IRS. They are completely solid-state units with no moving parts. Three-ring laser gyros replace the mechanical gyros in the older INS platform systems. This eliminates precession and other mechanical gyro shortcomings. The use of 3 solid-state accelerometers, one for each plane of movement, also increases accuracy. The accelerometer and gyro output are input to the computer for continuous calculation of the aircraft's position. The most modern IRS integration is the satellite GPS. The GPS is extremely accurate in itself. When combined with IRS, it creates one of the most accurate navigation systems available. The GPS is used to initialize the IRS, so the pilot no longer needs to do so. GPS also feeds data into the IRS computer to be used for error correction. Occasional service interruptions and altitude inaccuracies of the GPS system pose no problem for IRS Smart GPS. The IRS functions continuously and is completely self-contained within the IRS unit. Should the GPS falter, the IRS portion of the system continues without it. The latest electronic technology has reduced the size and weight of INS IRS avionics units significantly. Figure 11,156 shows a modern micro-IRS unit that measures approximately 6 inches on each side. Aircraft Communication, Addressing and Reporting System, ACARS. ACARS is a two-way communication link between an airliner in flight and the airline's main ground facilities. Data is collected in the aircraft by digital sensors and is transmitted to the ground facilities. Replies from the ground may be printed out, so the appropriate flight crew member can have a hard copy of the response. Installation of communication and navigation equipment. Approval of new avionics equipment installations. Most of the avionics equipment discussed in this chapter is only repairable by the manufacturer or FAA-certified repair stations that are licensed to perform specific work. The airframe technician, however, must competently remove, install, inspect, maintain, and troubleshoot these ever-increasingly complicated electronic devices and systems. It is imperative to follow all equipment and airframe manufacturers' instruction when dealing with an aircraft's avionics. The revolution to GPS navigation and the pace of modern electronic development results in many aircraft owner-operators upgrading flight decks with new avionics. The aircraft technician must only perform airworthy installations. The avionics equipment to be installed must be a TSO'd device that is approved for installation in the aircraft in question. The addition of a new piece of avionics equipment and/or its antenna is a minor alteration if previously approved by the airframe manufacturer. A certificated airframe technician is qualified to perform the installation and return the aircraft to service. The addition of new avionics not on the aircraft's approved equipment list is considered a major alteration and requires an FAA Form 337 to be completed. A technician with an inspection authorization is required to complete the approval for return to service following a major alteration and to sign the corresponding approval for return to service block on Form 337. Most new avionics installations are approved and performed under an STC. The equipment manufacturer supplies a list of aircraft on which the equipment has been approved for installation. The STC includes thorough installation and maintenance instructions which the technician must follow. Regardless, if not on the aircraft's original equipment list, the STC installation is considered a major alteration and an FAA Form 337 must be filed. The STC is referenced as the required approved data. Occasionally, an owner, operator or technician wishes to install an electronic device in an aircraft that has no STC for the model aircraft in question. A field approval and a Form 337 must be filed on which it must be shown that the installation will be performed in accordance with approved data. Considerations. There are many factors which the technician must consider prior to altering an aircraft by the addition of avionics equipment. These factors include the space available, the size and weight of the equipment, and previously accomplished alterations. The power consumption of the added equipment must be considered to calculate and determine the maximum continuous electrical load on the aircraft's electrical system. Each installation should also be planned to allow easy access for inspection, maintenance, and exchange of units. The installation of avionics equipment is partially mechanical, involving sheet metal work to mount units, racks, antennas, and controls. Routing of the interconnecting wires, cables, antenna leads, etc. is also an important part of the installation process. When selecting a location for the equipment, use the areas designated by the airframe manufacturer or the STC. If such information is not available, select a location for installation that will carry the loads imposed by the weight of the equipment and which is capable of withstanding the additional inertia forces. If an avionics device is to be mounted in the instrument panel and no provisions have been made for such an installation, ensure that the panel is not a primary structure prior to making any cutouts. To minimize the load on a stationary instrument panel, a support bracket may be installed between the rear of the electronics case or rack and a nearby structural member of the aircraft. Figure 11,157. Avionics radio equipment must be securely mounted to the aircraft. All mounting bolts must be secured by locking devices to prevent loosening from vibration. Adequate clearance between all units and adjacent structure must be provided to prevent mechanical damage to electric wiring or to the avionic equipment from vibration, chafing, or landing shock. Do not locate avionics equipment and wiring near units containing combustible fluids. When separation is impractical, install baffles or shrouds to prevent contact of the combustible fluids with any electronic equipment in the event of plumbing failure. Cooling and moisture. The performance and service life of most avionics equipment is seriously limited by excessive ambient temperatures. High-performance aircraft with avionics equipment racks typically route air-conditioned air over the avionics to keep them cool. It is also common for non-air-conditioned aircraft to use a blower or scooped ram air to cool avionics installations. When adding a unit to an aircraft, the installation should be planned so that it can dissipate heat readily. In some installations, it may be necessary to produce airflow over the new equipment, either with a blower or through the use of routed ram air. Be sure that proper baffling is used to prevent water from reaching any electronics when ducting outside air. The presence of water in avionics equipment areas promotes rapid deterioration of the exposed components and could lead to failure. Vibration isolation. Vibration is a continued motion by an oscillating force. The amplitude and frequency of vibration of the aircraft structure will vary considerably with the type of aircraft. Avionics equipment is sensitive to mechanical shock and vibration and is normally shock-mounted to provide some protection against in-flight vibration and landing shock. Special shock-mounted racks are often used to isolate avionics equipment from vibrating structure. Figure 11,158. Such mounts should provide adequate isolation over the entire range of expected vibration frequencies. When installing shock mounts, assure that the equipment weight does not exceed the weight-carrying capabilities of the mounts. Radio equipment installed on shock mounts must have sufficient clearance from surrounding equipment and structure to allow for normal swaying of the equipment. Radios installed in instrument panels do not ordinarily require vibration protection since the panel itself is usually shock-mounted. However, make certain that the added weight of any added equipment can be safely carried by the existing mounts. In some cases, it may be necessary to install larger capacity mounts or to increase the number of mounting points. Periodic inspection of the shock mounts is required, and defective mounts should be replaced with the proper type. The following factors to observe during the inspection are deterioration of the shock-absorbing material, stiffness and resiliency of the material, and overall rigidity of the mount. If the mount is too stiff, it may not provide adequate protection against the shock of landing. If the shock mount is not stiff enough, it may allow prolonged vibration following an initial shock. Shock-absorbing materials commonly used in shock mounts are usually electrical insulators. For this reason, each electronic unit mounted with shock mounts must be electrically bonded to a structural member of the aircraft to provide a current path to ground. This is accomplished by secure attachment of a tinned copper wire braid from the component across the mount to the aircraft structure as shown in Figure 11.159. Occasional bonding is accomplished with solid aluminum or copper material where a short flexible strap is not possible. Reducing radio interference. Suppression of unwanted electromagnetic fields and electrostatic interference is essential on all aircraft. In communication radios, this is noticeable as audible noise. In other components, the effects may not be audible but pose a threat to proper operation. Large discharges of static electricity can permanently damage the sensitive solid-state microelectronics found in nearly all modern avionics. Shielding. Many components of an aircraft are possible sources of electrical interference which can deteriorate the performance and reliability of avionics components. Rotating electrical devices, switching devices, ignition systems, propeller control systems, AC power lines, and voltage regulators all produce potential damaging fields. Shielding wires to electric components and ignition systems dissipates radio frequency noise energy. Instead of radiating into space, the braided conductive shielding guides unwanted current flows to ground. To prevent the buildup of electrical potential, all electrical components should also be bonded to the aircraft structure ground. Isolation. Isolation is another practical method of radio frequency suppression to prevent interference. This involves separating the source of the noise from the input circuits of the affected equipment. In some cases, noise in a receiver may be entirely eliminated simply by moving the antenna lead-in wire just a few inches away from a noise source. On other occasions, when shielding and isolation are not effective, a filter may need to be installed in the input circuit of an affected component. Bonding. The aircraft surface can become highly charged with static electricity while in flight. Measures are required to eliminate the buildup and radiation of unwanted electrical charges. One of the most important measures taken to eliminate unwanted electrical charges which may damage or interfere with avionics equipment is bonding. Charges flowing in paths of variable resistance due to such causes as intermittent contact from vibration or the movement of a control surface produce electrical disturbances, noise, in avionics. Bonding provides the necessary electric connection between metallic parts of an aircraft to prevent variable resistance in the airframe. It provides a low impedance ground return, which minimizes interference from static electricity charges. All metal parts of the aircraft should be bonded to prevent the development of electrical potential buildup. Bonding also provides the low resistance return path for single-wire electrical systems. Bonding jumpers and clamps are examples of bonding connectors. Jumpers should be as short as possible. Be sure finishes are removed in the contact area of a bonding device so that metal-to-metal contact exists. Resistance should not exceed 0.003 ohm. When a jumper is used only to reduce radio frequency noise and is not for current-carrying purposes, a resistance of 0.01 ohm is satisfactory. Static discharge wicks. Static discharges, or wicks, are installed on aircraft to reduce radio receiver interference. This interference is caused by corona discharge emitted from the aircraft as a result of precipitation static. Corona occurs in short pulses, which produce noise at the radio frequency spectrum. Static discharges are normally mounted on the trailing edges of the control surfaces, wing tips, and the vertical stabilizer. They discharge precipitation static at points a critical distance away from avionics antennas, where there is little or no coupling of the static to cause interference or noise. Flexible and semi-flexible discharges are attached to the aircraft structure by metal screws, rivets, or epoxy. The connection should be checked periodically for security. A resistance measurement from the mount to the airframe should not exceed 0.1 ohm. Inspect the condition of all static discharges in accordance with manufacturer's instructions. Figure 11160 illustrates examples of static discharges. Installation of aircraft antenna systems. Knowledge of antenna installation and maintenance is especially important, as these tasks are performed by the aircraft technician. Antennas take many forms and sizes dependent upon the frequency of the transmitter and receiver to which they are connected. Airborne antennas must be mechanically secure. The air loads on an antenna are significant and must be considered. Antennas must be electrically matched to the receiver and transmitter that they serve. They must also be mounted in interference-free locations and in areas where signals can be optimally transmitted and received. Antennas must also have the same polarization as the ground station. The following procedures describe the installation of a typical rigid antenna. They are presented as an example only. Always follow the manufacturer's instructions when installing any antenna. An incorrect antenna installation could cause equipment failure. Place a template similar to that shown in figure 11161 on the fore and aft centerline at the desired location. Drill the mounting holes and correct diameter hole for the transmission line cable in the fuselage skin. Install a reinforcing doubler of sufficient thickness to reinforce the aircraft skin. The length and width of the reinforcing plate should approximate the example shown in figure 11162. Install the antenna on the fuselage, making sure that the mounting bolts are tightened firmly against the reinforcing doubler and the mast is drawn tight against the gasket. If a gasket is not used, seal between the mast and the fuselage with a suitable sealer, such as zinc chromate paste or equivalent. The mounting bases of antennas vary in shape and sizes. However, the aforementioned installation procedure is typical of mast-type antenna installations. Transmission lines. A transmitting or receiving antenna is connected directly to its associated transmitter or receiver by a transmission line. This is a shielded wire, also known as coax. Transmission lines may vary from only a few feet to many feet in length. They must transfer energy with minimal loss. Transponders, DME, and other pulse-type transceivers require transmission lines that are precise in length. The critical length of transmission lines provides minimal attenuation of the transmitted or received signal. Refer to the equipment manufacturer's installation manual for the type and allowable length of transmission lines. To provide the proper impedance matching for the most efficient power transfer, a balun may be used in some antenna installations. It is formed in the transmission line connection to the antenna. A balun in a dipole antenna installation is illustrated in figure 11,163. Coax connectors are usually used with coax cable to ensure a secure connection. Many transmission lines are part of the equipment installation kit with connectors previously installed. The aircraft technician is also able to install these. Connectors on coax. Figure 11,164 illustrates the basic steps used when installing a coax cable connector. When installing coaxial cable, secure the cables firmly along their entire length at intervals of approximately 2 feet. To assure optimum operation, coaxial cables should not be routed or tied to other wire bundles. When bending coaxial cable, be sure that the bend is at least 10 times the size of the cable diameter. In all cases, follow the equipment manufacturer's instructions. Maintenance procedures. Detailed instructions, procedures and specifications for the servicing of avionics equipment are contained in the manufacturer's operating manuals. Additional instructions for removal and installation of the units are contained in the maintenance manual for the aircraft in which the equipment is installed. Although an installation may appear to be a simple procedure, many avionics troubles are attributed to careless oversights during equipment replacement. Loose cable connections, switched cable terminations, improper bonding, worn shock mounts, improper safety wiring, and failure to perform an operational check after installation may result in poor performance or inoperative avionics.